Hey everyone, welcome back to my channel and another new video. This is the most important video of the complete data structures, algorithms and interview preparation bootcamp that we are doing, because in this video we're going to look at binary tree interview questions. So binary search trees interview questions. So this is one of the most important topics if you are applying for like Google, Microsoft, Facebook, Amazon, Apple, all the big tech companies, because binaries, it's one of the most widely asked topics in interviews. And it's also one of the easiest. You may have seen many memes like invert a binary tree meme and all sorts of things. And people say that, okay, it's a difficult topic or whatever. Let me tell you right now, if you're new to the community, if you're new to the channel, I'm doing a complete data science algorithms bootcamp, and I did a binary search video which is close to 1 million views. Why? Because binary search is also one of the most important topics asked in interviews. So I made a binary search interview questions video which is going to cross 1 million views, and it is one of the best videos that you can watch for binary search, right? So this binary search video that I've already made, the whole idea behind the videos that I make is because the mistake that I see students make is, and you might be making these mistakes, is when they're studying data structures algorithms, preparing for interviews, practicing on lead code is okay, highly recommended. But when they're watching tutorials, oftentimes the biggest mistake that students make is they watch a lot of videos of individual topics. Many people have made their playlists, like there would be an entire playlist on, let's say, dynamic programming, entire playlist on trees, and in that entire playlist, they will solve every single each question in like 15-20 minutes video. Okay, we solve 20-30 questions on trees. Why that is a bad idea is that you are only focusing on those 20-30 questions. That is not how you prepare for your interviews. Okay, what if someone gives you a newer question? So if someone is teaching you, okay, this is a nice binary tree questions, let's say diameter of binary tree, this is how you solve it and etc., that is not going to help you. Because if someone gives you a newer question, let's say slightly modified, you will get scared, like, oh, this type of question I may not have done before. So Kunal, what is the right approach then? The right approach is the one that I've already followed in the previous videos, and I'm going to follow in the future as well. Like the binary search video I did, questions video, stack and queue questions video, linked list question video, recursion questions video, object-oriented programming. So the right way to approach these sort of, like when you're preparing for your interviews, is look at the thought process and why you are solving the question while you are solving it. I never make playlists like this, like 20-30 questions individual videos. People do this because it's good for their YouTube video engagement or whatever. Instead, what I will do is I will only make one video, just one tree video, which is this one, the questions ones. Okay, theory I have explained in previous sections. So previous videos, you want to check out how trees work and implementation, you can check that out. But regarding interview preparation questions, only one video I will make. And this one video will help you solve any tree question. Same thing for heaps. The next video will be on heaps. I will make one introduction to heaps, like what are heaps, how heaps work, time complexity, etc. And only one video on heaps questions. So Kunal will only teach you everything you need to know to solve any tree interview question only in one video. I don't do things like, okay, 20-30 individual videos, 15 minutes. No, I will only teach you, let's say I will solve 20-30 questions, but behind every 20-30 question, I have spent, let's say for this tree video that I'm making right now, full disclosure, I have spent close to 1 month researching. So I looked at like the past decade and I looked at all the patterns, and I spent close to 1 month, like 3 weeks or something, more than that. So 1 month I have spent analyzing what sort of patterns and what sort of questions do companies ask when it comes to trees. So we will definitely be solving trees questions, that is no doubt, but that is not the priority for us. The priority for me is going to be why. Talking about invert a binary tree, we will look at the solution. Secondary, we will look at the solution later. First, we will think about why we are approaching this question like we are approaching it. What made us think that we are going to apply this algorithm in this type of question? That is how it's going to help you clear any tree interview. Because when you're given a new question, doesn't matter what question it is, lead code, easy, medium, hard, very hard, extreme, you will see, okay, this is the sort of question that we are getting, this is what we need to do. Kunal taught us that if this sort of approach is given to you, this is what you need to apply. If this data is given, apply this sort of algorithm. That thought process building is very important. This is going to be much more beneficial than watching an entire tree playlist on hundreds and hundreds of questions. You don't want to do that. That is too much spoon feeding. You don't have to do that. Very bad thing. Instead, only watch the thought process, of how things are working. Rest, use that and then practice. Speaking of practice, you can find the assignment links in the description below and solve those assignments. People ask where are the solutions to those assignments. So these are lead code problems. You can find the solutions on the lead codes discussion tab. So you can find it over there. And yeah, make sure one last thing, make sure you like, share and subscribe, join the Learning in Public initiative. Make sure you comment at least. These are free videos that I'm making, so the best way by which you can help me is sharing it with other people and commenting at least and liking it. So like and comment, I highly recommend you to do like right now, and sharing if you want. You can use hashtag DSA with Kunal, share it on socials, Twitter, LinkedIn, whatever you want. Not many people will share, that's fine, but at least everyone can like and comment. Yeah, very excited. Let's get started. And trees is one of the most easiest topics, don't worry. In data structure algorithms and interview preparation, every single topic is easy. Only two are difficult. Dynamic programming and graph theory, these are difficult topics. Not really difficult, but challenging. Rest, everything is easy. Trees, piece of cake. It's a joke, actually, if I'm for lack of better words. Tree questions that Google asks, that Facebook asks, Amazon's and all these companies ask, these are very straightforward and not that difficult if you are done with the right preparation. So yeah, let's get started. Okay, so when it comes to binary search trees or binary trees, there are two most important topics for your coding interview preparation. 99% of the chance that you will get questions from these two topics, these two patterns that we're going to learn about today. Very popular, many people have heard of it. Breadth first search and depth first search, BFS and DFS. First, we're going to talk about BFS. It's very simple as the name suggests. I will also tell you when to use this sort of approach and how to identify that this approach is being used in the question. So you will be given binary tree, like let's say not a binary search tree but normal binary tree. And if you want to print this binary tree in level order, print it in level order, that is known as breadth first search, because you're searching along the breadth of the tree. So if you want to read this tree, print this tree, traverse this tree, it will be in this order. 1. So first this level, then this level, then this level. So 1, then 2, 3, then 4, 5, 6, 7. Okay, very easy. That is it. This is breadth first search. So you're searching from the top, you're starting from the root, but you're searching level wise. Okay, not a problem. We will see how to code this using recursion and iteration, very simple stuff. That's it. That's the breadth first search algorithm. I don't know how easier to explain this. That's it. Just go breadth by level. That's it. Okay. Okay. Now the main question, when to use this? So there are two cases. Case number 1, when answer lies near the root node. Any question you are given in tree where you think the answer will lie near the root node, use breadth first search. I'm telling you how to approach breadth first search type questions. Number 2, when you are asked to search by level, it's pretty self-explanatory. Like, the breadth first search, you're searching level by level. So in some cases you will be like getting questions in which you are doing some operations level wise. So a good question can be something like, let me give you a question. I'm an interviewer, I'm giving a question. You're given a binary tree and you have to compute, you have to calculate the sum of all the nodes at every level. So the sum of this level will be what? 1. Sum of this level will be what? 2 plus 3, 5. Sum of this level will be what? Something. Okay. Now you're like, okay, we are doing something by each level. Automatically it will click in your brain. We have to use BFS. Okay. Easy. Sounds good? So these are, if in any tree question you are given these two approaches, like these two things it is asking you the question, 99% of the time BFS will be used. Alright, so I won't waste any of your time. I will just get on with the explanation part on how to code this and do some nice questions. Okay, so let's say you have a question, simple tree I'm taking again, let's say 1, 2, 3, 4, 5, 6, 7. What is a simple way to do this? Like not a very optimized approach. What you can do is, or I can just add in another one over here, 8, 9, 10 here, 14 here. I can take 11 only, not a problem. So what you can do is you can calculate the height of this tree. Okay. And then for every level you can traverse, you can print like every level, and it's going to be very complicated, you know, if it's not optimized. Think about it, how you will do it. You have to print level by level. So you can calculate the height of the tree and then you can traverse it recursively and keep printing nodes at every level. You can maintain a level counter if you want, right? So height 1, height 2, height 0, height 1, height 2, height 3, height 4. So you can do that for every level. And worst case scenario, that will be n squared. In the case of a tree that is not balanced, like a simple, you know, single line tree like this one, you know, skewed tree. These are known as skewed tree. We've done this when we learned about AVL and everything. We did this already. Think about it, how you can do an optimized approach, breadth first search. Try to pause this video and do it. Okay, so let's get started. Breadth first search, very simple algorithm. Okay, so let's think about it. Let's see how we can, like, did you really think about it? Did you actually try to do it on pen and paper? You should. So always try to understand the problem first, then approach it. So the problem is print level by level. Okay, what are some of the facts? Always lay down the facts first, like some things that are obvious. This is how you approach coding interview problems. So the fact is, I will start from the root node. Start from here. That is a fact. I'm only given root node, I will start from root node. Now, via every node, I can access its children. So if I'm at root node, I know that I can access 2 and 3. I can just say node.left, node.right. Okay. Then I will go on the left hand side. Let's say if I go on node.left, I can again access node.left, which is 4 and 5, and node.right, which is 5. But then 3 is missing. I want to print 1 and then I want to print 2 and 3 together. So maybe I can print node and then I can print node.left, node.right. Okay. Then I will go in node.left. I will print node.left 4, node.right 5. But then how will I get this 3 again? I need to get this 3 again. How will I get to this pointer? Understand, right? So whatever answer you are given, try to replicate that. Answer I know is I am at the root node first. So I will just print root node. Not a problem. Simple. Then I will just say, okay, now I will print node.left, which is 2, and I will print node.right, which is 3. Okay, not a problem. Now my pointer, I can just put my pointer to node.left. Okay, now node was here. Now node will be here. So I can say, okay, now print node.left, node.right, node.left, node.right. But now the question is, how do I get to 6 and 7? In order to get to 6 and 7, I have to get where? I have to go to 3, because then I will be like 3.left, 3.right. But from this point, how do I get this? I can't go back. So how do I get to this 3? Now we are stuck. So if I want to get to 3, if I can get this node, I can easily get to it. So I'll store this node somewhere. Okay, that's the only approach. I will store it somewhere. Let's say I store it in an array or something. No problem. I stored 3. So then I can be like, okay, let's say I'm storing every level or every child. So when I printed, let's try again now. I print 1, and after I print 1, I will put the children of 1 in the array or whatever it is. 2 and 3. Now, this level done. Next, I will see in the array what do I have. I have 2. So I will get 2. I will print it and will put the children of 2, 4 and 5 in here. Then I will get 3. Now you can see I got 3. And I will put the children of, I will print 3 and I will put the children of 3 in here. Six and 7. Now again I will print out again from this element, like this array, 4. And I will put the children of 4 over here, 8 and 9. Easy. So you see my thought process how I did this. And this is actually not an array. I mean, it is technically an array, but you can see what it is happening. What is happening over here? First in, first out. This is Q. Is this not Q? We have done Q, stacks and queues. So we started the problem. We were like, okay, we are having difficulty accessing the previous elements in order. So I will just store that somewhere in order as I see those. And that's it. Now I will remove. I removed 4. I added the children of 4, 8, 9. Then I will remove 5. No children. Okay. Then I will remove 6. Only one child, 10. Then I will remove 7. Only one child, 11. Then I will remove 8. Then 9, 10, 11. See? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Level order traversal done. Very simple. Piece of cake. What do I want you to do? Now I want you to code this on your own. You know about queues. You know about everything. So how are you going to store level by level? Every level you can store in a list. We have done an array list before. Please, if you're new to the channel, watch the data structures bootcamp from the start. When we do dynamic programming and stuff, I will not be explaining you recursion. I've already made a complete playlist on recursion. So right now, don't expect me to explain to you queues. If you don't know queues, do 2 things. Think about what you're doing with your life. Point number 1, quit this video, sit on a chair, think about what you're doing with your life. If you're preparing for interviews, you don't know queues and you're following this playlist. And thing number 2 is go watch the queues, stacks and queues videos, stacks and queues theory and questions video. So queue, very simple. What I can do is I can save every level in a list. So I can save, if it's a list of list, first list can be 1, second one can be containing 2 and 3, third one can be containing 4, 5, 6, 7. So instead of printing like this, I can just store it in a list, so on and so forth. Okay, so list of list you have to return, and just array list is fine, and that is it. Try to code it on your own, but if you still can't do it, which I think you should be able to do it because I just told you everything, then I will show you right now. Before I move forward with that, what is the time complexity? We are visiting every node only once. If there are n number of nodes, then time complexity is O of n. What is the space complexity? What is the maximum number? Not talking about, let's say, the output array. Okay, let's say you're only displaying it. So in that case, in the queue, what is the maximum number of elements we can have? N by 2. How? Tell me. We are storing every level in the queue. You all know that. And when we have a balanced binary tree, you all know what a balanced binary tree is. We have done binary tree theory lecture. In the balanced binary tree, all the leaf nodes will be full. What is the number of leaf nodes? N by 2. You need proof of n by 2? Watch the binary tree video I did, theory. So time complexity O of n by 2, constants are removed, O of n. Sorry, space complexity O of n by 2, constants are removed, so O of n. time complexity O of n because we are visiting every node only once. Simple, easy. Okay, same question on lead code. Order level order traversal, you have to return a list of list, just like I mentioned. And gonna create a new file. By the way, you can find the code samples in the description below. And you can directly run it on your browser and stuff, so easier for you to set up and all these other things. Close, class main, zoom in. I will just copy this method. Okay, we are given root node, return list of list. What are we doing? We are starting from the root node. We need a list of list first. Result is equal to new array list. Okay, generics we have already done. In the end, just return the result. Now, we do what? What do we do? Just look at the diagram. First of all, if the tree is empty, so if it is null, then just return the result, empty list. Now I'll start from the root node. I have to have a queue. So I can get a queue of type what? Tree node. Queue is equal to new. You can have queue over here, but you cannot do new queue. You have learned about stacks and queues, new linked list. You'll be like, now Kunal, what are you doing? What are you doing? You're making queue is equal to linked list. How is that working? Please watch the object-oriented programming playlist. Do not waste time. New linked list. Initially, queue is going to have what? So while we are removing items from the queue, we are displaying those. That's what we're doing, right? So initially, it will just have root node. Queue.offer root node. Easy. Now, what do we do? While queue is not empty, we are going to do something. While not queue dot is empty, what are we going to do? Initially, let's say it only has 1 in it. So I know that the level size is equal to the queue size. Is that not true? So level size right now is equal to 1. I will just run a loop equal to the level size. Let's say I printed 1, then I added over here. Let's say I added over here now 1 is removed. And while I removed it, I added 2 and 3. So you can see while every level is finished removing from the queue, the remaining elements is going to be equal to the size of the next level. So now the size of the next level is 2 and 3. So I will keep removing till the size of the next level. So I will keep removing only 2 elements. And while I'm removing that, I will add other elements. So I remove 2. I will add 4 and 5. I remove 3. I will add 6 and 7. I will only remove 2. Then I will go to the new level. Size of the new level is now, after removing 2, whatever size is remaining. 4. That is true. Size of next level is 4. That is true. Okay. So int level size is equal to what? Q.size, that is the level size. Now I will just run a loop. For int I is equal to 0, I is less than level size I plus plus. What am I going to do? I'm going to say that get me the current node that you're working with. So tree node, current node is equal to q dot poll. These all the queue methods and everything we have already done, push, pop, and stack and all these other things. So I got, let's say I removed 1. I will have to add 1 in another list. So this bigger list is the result list. And this is the current level list. So current level list I have to create. Okay, not a problem. Every level will have a current level list. Current level list. Okay, can have it as a size array level size. No, not a problem. So I will get one node and I will put it in the current level. Current level dot add current node dot, is it value? What is it? Val. Current node dot val. So this will traverse all the levels, and then while I am removing, I have to also add in the queue. So you see, remove 1, add 2 and 3. Remove 2, add 4 and 5. But only add when it is not null. I don't want it to add null. I don't want it to display null in the integer or whatever. It will give me null pointer. So I can say if current node dot left is not equal to null, add it. If current level dot, so I can just say q dot offer, which is going to add it, current node dot left. This way I can access these nodes. Similarly, if right is not also not empty, add the right one. So this loop will make sure that every single level is being, so after this loop is finished executing, my current level will have a level. So that I can just add it in the main answer. Result.add current level. That's it. Done. Simple. Copy paste. In this video, we'll do a lot of copy paste. So all these problems will be solved via this approach. How cool is that? Difficult to difficult problem, complex to complex problem, just via breadth first search, this algorithm. Paste. Then we'll run it. Okay, I'm going to submit. Looks good. Accepted. 1 millisecond beats 94%. So pretty good enough. Not a problem. All right. Try it yourself. And that was it. How simple was that? Just follow whatever is given on the diagram. Okay, it's very simple. Next question. Okay, it's next question over here. Again, lead code, pretty simple. Question is given average of levels in binary tree. This single word, levels. This single levels word tells me that I have to use breadth first search. Exactly copy paste. Given the root of the binary tree, return the average value of the nodes on each level in the form of an array. Each level, okay, 100% BFS will be used. So instead of, I'll just copy paste. It will be list of double. New array list. Okay, and here basically you can see that for every level, I don't need to maintain current level. Okay, so I'll just say current node is equal to q.poll, and instead of that, because I don't need to store every level, right? I just need to get the what? Average. Okay, just need to get the average. So instead of storing it in a level, I can just get double average, initially 0, and I can just say return dot average of level. See, copy paste. I don't even have to explain this question. There's nothing to explain in this question. In the previous question, we were storing every level in a list. Now we're just not doing that. Exactly copy paste. Instead of storing in another list, I'm just calculating the average. So for this entire level, I will say just calculate the average. Okay, that's it. Let's do that. So what is the average going to be? So I will say average level is equal to current node dot value. I will just plus current node dot value. I will just add this. You'll see what I'm doing. It's very simple. So I have now the sum of all these levels. This is actually sum of all the levels. So if you're given a question, sum of all the levels, there you go. But in the end, I will just take an average of this. So average of this is going to be average of level divided by the level size. Simple. Submit this. Accepted. Memory beats 92%, runtime beats 97%. How simple was that? Literally copy pasted. Okay. So what did I do? See, level size, etc., everything same. But whenever I'm going to a new level, so I say remove 1 from the queue, 1 is removed. So average of level 1 is equal to 1. Now it added 2 and 3 in it. Level size is equal to what right now? Level size is equal to 2. So when it goes inside this loop, average level is going to be equal to currently 0. It will remove 2 from it. Average level size, average level right now is going to be equal to 0 plus 2, 2. And then it's going to add in the child of 2. So 4 and 5. Then it's going to remove 3. 2 plus 3, it's now going to be equal to 5. And it's going to add 6 and 7 in it. 6 and 7 added in it. Loop over. So it will come out of here. Then average level is going to be equal to whatever sum you have divided by the level size. So it will divide it by 2. Give me 2.5. That is correct. Simple. Easy. So instead of average level, I can put this as this is actually level sum. Or no, because then I'll have to take another, it's fine. Easy. You see this question that we just did, average of tree levels, is asked in Google. Is this actually a question? The thing that confuses me is how the person would have they must have asked other questions, because if 45-minute interview, this question would take 3 minutes to explain. If you're trying from brute force first, 2 minutes to code. So 45 minutes, I think 5-minute question, and then they must have asked some other questions. So very simple. All right, moving forward. Now the next question, again asked at Google. Very simple. Given a binary tree, 3, 4, not a binary search tree, okay, binary tree, random. 8, 12, 14, 36, 9, 7, 'something like this. You have to do level order successor. So you're given the root node and you're also given, let's say, a value, let's say you're given 14. So the answer for 14 you're given 14. So the answer for 14 is going to be equal to level order successor. It basically means you're given a value, give me the value that is right next to it. Okay. If you're given 14, answer is what? What is right next to 14? 7. Answer is 7. You're given 11, then answer is, what is right next to 11? Nothing. 36. That's it. Is this not also copy paste? Do you have to even think about this question? No. It is breadth first search. We are not storing anything, we are not calculating anything. So whenever we find an element, I know that in the queue of breadth first search, the items are in level wise order because I keep removing them and it forms one level. So 12, 14, 7, 11 will be in the queue. So whenever I am removing items from the queue, I know that the next item in the queue is actually the one that is right next to it. So whenever I'm removing an item from the queue, if that item is equal to the one that is given to me, I will stop my program there and I will return the next item in the queue. For example, initially the queue has 3. I will say, is 3 the one you're looking for? Let's say we go for 14. Is 3 the next you're looking for? No, I'm looking actually for 14. Okay, so I will remove 3, add in the children. 4 and 8 will be added. Now 4 will be removed. And is 4 the one I'm looking for? No. Okay, 12 and 14 will be added. 8 will be removed. Sorry, is 8 the one I'm looking for? No. 7 and 11 will be added. 12 will be removed. Is 12 the one I'm looking for? No. No children, moving on. 14 will be removed. Is 14 the one I'm looking for? Yes. 14 is the one I'm looking for. So I will add in the children at least, just so that let's say there was nothing here. So I will not just return the what is next because it might be empty. Okay. I will tell you one second. So 14 is the one I'm looking for. I will add 36 and 9 and I will just return whatever the next item is, just this. So the question is very simple. So now the question is, why did I not just return the next item and why did I wait for adding the children of 14, 36 and 9? Because for example, let's say you did not have this thing. In that case, you will not also have this thing. So you remove 14 and you're like, okay, return the next item. Next item is null. You will just return empty. You'll be like, it is the empty. So that is why we first need to add the children and then I will return whatever the next item is, which is now 36. So in this case, the next item would be 36. So this was the doubt, like why are you adding the children first and then stopping the program? Make sense? Okay. Copy paste, nothing new. Exactly copy paste, nothing new. Question was asked in Google. So funny. Kind of funny. Okay, let's say I create the method. I hope you can see that. Public. Okay. I have to find this, let's say I'm returning the node itself. Tree node, find successor. Tree node root and int, let's say we're giving it a key. If first of all root is equal to null, I will just say return null. Node does not exist. Oh. Looks good. Okay. And otherwise, just copy paste. First of all, I promised you that we will not write any code. So I'll do one thing, I'll just copy paste. I'll remove the code that I have written. I'll copy paste. So let's see. Don't need this. If root is equal to null, return null. I need the q. Q added root, no problem. I will, level size is fine. I don't need the average. I don't need to average. Current node is going to be equal to this one. And I will add the children. After adding the children, I've added the children in, but I don't need a for loop either. Because here I did not have a for loop. I'll just keep removing. I don't need to maintain how many elements are there in the level. Don't need the for loop. No need for for loop either. No need for average. No need to add in result. Return null. So when you're added, and if that current node that you have removed is equal to the one that I want, I will just stop the program. In the end, I'll just remove whatever is next in my queue. Done. That's it. And you're also aware of the time complexity, space complexity of what all these things are happening. Space complexity may change based on the answer. Time complexity O of n. Okay, if you're not using any extra space. But here, since we are using q, so it's going to remain O of n only. Till the time you're using this extra q, it's going to remain O of n. Okay, because it's going to maximum ny2 elements in the binary tree, like when all the leaf nodes are full. So for all these questions, space complexity O of n, time complexity O of n, which is very good. Moving on, next question. I'll zoom in a little bit so you can see, very simple. By the way, code link can be found in the description, so check it out, 4kit, and just all the links can be found in the description. You can check it out once. Okay, next question. It says binary tree zigzag level order traversal. This question has been asked in Google, Amazon, and Microsoft. It's a joke. You can see 10,000 thumbs up. This question is nothing. This is a very easy question. Copy paste, literally, just little bit different. Okay, so question is simple. You have to print it zigzag manner. So it says level order traversal. So breadth first search will be used. But how do we print it in zigzag order? Let's see. Let's say you're given a tree. You're given normal tree. Okay, something like this. You have to print it in zigzag order. Means first you have to print 1. Print 1. Why is it not changing my color? Okay. Print 1. Then print it like this. Then like this. Then like this. So answer should be 1. 3, 2, 4, 5, 6, 7, 11, 10, 9, 8. Not a problem. I can do that. And here you can see that every alternate. So what you have to do is think about what is happening. We know breadth first search will be used. One more pointer I would like to give you is when you know a certain algorithm is being used. Like I know here breadth first search will be used. Try to solve it using breadth first search and see how you can modify it. I will try solving using breadth first search. So in my queue I will have 1 and I will be like, okay, I will just print 1, add in 2 and 3. Not a problem. Now what I have to do is I have to print this whatever I have level now left in the array in the queue. Whenever level is finished, I will have next level left in the queue. We know that. So level 1 finished. Now I have another level left in the queue. I know that this level I have to print in reverse order. I have to print this level in reverse order. So instead of removing from the front of the queue, I have to remove from the back of the queue. So let's say I can remove from the back of the queue, then I will just remove 3. Where will I add 6 and 7? Again, remember that if I add 6 and 7 in the behind, then I cannot remove 2 because I am removing items from the behind. So I will just add 6 and 7 in the front. See, now if I add 6 and 7, then I cannot remove 2 because then it will remove 7. I will add 6 and 7 here, then I will remove 2, 2 will be printed, and I will add 4 and 5 here. Now I'm in the regular order again, so I will remove 4 normally, 4 printed, I will add 8 and 9, so on and so forth. 5 removed, I will add nothing. 6 removed, I will add 10 and 11. 7 removed, I will add nothing. Now again I have to print. Now again I'm in the reverse order. So in the reverse order, what I'm doing is I am removing from the left. Very simple, problem solved. So normal order, what you have to do is remove from front, add in back. Reverse order, remove back, add in front. Simple. You see how I came to this approach. I started using breadth first search, then I sort of like just modified it by doing what the question is asking me to do. I explained to you my thought process also. I can do this using dec or dq in Java. Dec or dq, it's pronounced dec, but you can call it dq also, whatever you like. In that, q is first in, first out. In dec, you can add in and remove from either of the sides. Simple, that's it. So in constant time, so from the front or the back, you can remove, not a problem. That's it. And I can just maintain a pointer, not a pointer, a flag, that when I'm in reverse order, so reverse for this will be equal to true, then reverse will be equal to false. This way I know when I need to start adding from the back. Then again reverse will be equal to true. Initially reverse will be equal to false. Okay, let's try to code this. Okay, so dec will be using, and you can Google it as well, Java dec or dq. Here you can find all the answers. See, add first, remove first, add last, remove last. It maintains a tail. Okay, add first, remove first, add last, remove last. We will use this. Copy paste. Then let's say we copy paste the initial solution of level order traversal. It's all copy paste only. This whole entire thing we're doing is, everything is game of copy paste. Okay, few things we need to change. Few things we have to change. Maintain, first of all, this will be dq. Okay, here we are using dq. So dq or dec, QUE, that's it. I've added root node in, not a problem. After adding root node in, I will maintain a reverse. Boolean reverse initially is equal to false. I will get the level size, not a problem. And while my queue is not empty, I will, this is my current level, which is fine. Okay, current level, which is fine. And here I will say there are two cases, normal order, reverse order. So if normal order means not reverse, and if reverse, okay, or I can just say else. And after that, I will also say, after this thing, I have to switch it. So if reverse is false, next time it runs the loop, for the next level, it will be true. So reverse is equal to not of reverse. It's just flipping it. If it is not of, so I will just do this. If it is normal, then it will do it normally. Okay, if it is in the normal order, then remove from front, add in the back. So removing from the front, okay, or I can be more specific, pole first, add it in the back. Okay, current node offer, right? Add it in the back, or I can just use add last also, just to make it clear to you. Otherwise what? Remove from back and add it in the front. Pole back, add first. That's it. Okay, one thing here, it will be pole last. And also one more thing, when I'm adding, let's say in the reverse is true, I'm adding, I say I removed 3, so I was adding 6 and 7. If I'm adding from first, I will first add the right and then I will add the left. So for example, if let's say I removed 3, and here I need to add 6 and 7 in the first. So if I add left first, see what will happen. Left added first, see, write it down again. Say I removed 3, then I need to add children of 3. So 6 and 7. So it says remove from the back, add in the front. So let's say I add in the front 6 first, left, and then I add 7. So this is here in opposite order. I wanted 6 and 7, it is giving me 7 and 6. Instead, I will add 3 dot right first and 3 dot left later. 3 dot right is 7, 7 added first. 3 dot right is 3 dot left, 6, 6 added later. So just swap this. Okay, that's it. Copy paste and let's submit it. Okay, and after every level, so after this for loop is for one level. After that, I will do the reverse, not reverse. Copy pasting this, I will paste my answer here and submit it. Should be fine, accepted, and runtime is also good. Memory is also nice. Cool. Google, Amazon, and Microsoft. Nice, pretty easy. Let's move forward. Okay, now similarly, now it's asking level order bottom. Also very simple question. It's saying given the root of the binary tree, you are doing level order traversal, but print it in reverse order. Print it in reverse order, like store it in the array in the reverse order. First you are storing 3, then 9, 20, then 15, 7. It's saying no, do it in reverse order, 15, 7, 9, 23. It's very simple. In the overall answer, when you're adding, instead of adding items one by one in the next order, like first I added 3, then after 3 I added 9 and 20, then after 9 and 20 array I added 15 and 17. Instead I will add it at the 0th index before. So actually nothing you have to do. Level order copy paste, add at the 0th index. So list has an add method. You can specify index and that's it. Submitted. Memory beats 98%. Runtime beats 94%. Very simple. Did you even have to do anything else? I just added 0. Very simple. Okay, moving forward. Okay, next question is interesting because it's a relatively new one that was asked. This question was asked in Amazon London last year, so 2022. Amazon London software development role. This question is, you will laugh at this question. It's actually copy paste again. All the questions are copy pasted. Doesn't matter if it's being asked in California, Google London, Facebook Meta, Amazon Microsoft. All these questions, if you know the basics, you can do. All right. Perfect binary tree is given. All the leaves are on the same level. Very simple, not a problem. You have to, and also every parent has 2 children. Populate next right pointer in every node. So let's say, for example, this tree is given to you. Then on the level, every level, just you have to connect every node. So 2 will be connected to 3. Similarly, 4 will be connected to 5. 5 will be connected to 6. 6 will be connected to 7. So you can see every level is being connected to each other. Not each other, but like every node in every level is like forming a train, a linked list, if you will. Every level is a linked list. Okay, that's what you have to do. So every node has this property left and right, but they have added one more property called next, which will be to the next of their level order traversal. So we know something is happening level by level. So we know breadth first search will be used. Okay, how will it be used? What can you do? One thing you can do is again save all the levels like we were doing in the current level queue. We were doing that, or the array, sorry, not the queue. In the current level array we were doing, we can store it that way, and then we can connect all of them in the, so we know that at a particular, after you're done traversing a level, I know that in the queue, that next level will be remaining, I know that. So using that queue, you can just connect all the elements in that queue. But the problem here is, it is what we are doing so far. It will take O of n complexity. You know how, right? O of n by 2, space complexity, O of n by 2. Can we do it in constant complexity, like no extra space needed? Let's see. Okay. Actually, this is a good question. I like to give credit where credit is due. From the approach that I have taught you right now, you can do this very easily. But the problem is, then the interviewer will be like, okay, that is O of n space complexity, O of n time complexity, O of n space complexity because you are using a queue. Can you do it using without queue? That is the question. To pause this video, think about it, how you can do it without using the queue. And if you're not using queue, you will be using some pointers. So try to think about that. You'll start from the root node. You cannot use a queue. And you have to connect all the level wise. So think about it. Think about the thought process. You know how we approach questions now? You see what we need to do. We lay down all the things that are obvious, and then we try to work towards the final problem. And we also try to see things that are given to us. It's a very important part. Many people forget that. Okay. So think about things like this. How will the problem end? What is the end case? And how will I know that it is ending? All sorts of questions should run through your mind. Okay. Okay, let's see how we can solve this. I will tell you how I'm approaching this question. Okay, I will tell you my secret. It is not really a secret. Listen to it very carefully. It is very important. Because I have told this secret when I was teaching linked list. What is the secret? Secret is when you're given questions like this, in which you have to do something that they are asking you to do. It doesn't require any brainstorming. It's not like, okay, this guy has 5 mangoes. They have to distribute a particular mango into a group of table like this and that. And you have to have like permutation, combination. There are, let's say, n number of cows. Every cow needs to give this much amount of milk. And this is how you will calculate that milk and you will make. So, such questions are like, oh, wow, so much to think about over here. so much to think, like, so many mathematicals is also involved and every stuff like that. But there are certain problems like this that you don't have to think, because they are asking you to do something. As you can see over here, they are saying do something that is just given over here. Linked list is one of the most popular topics in this sort of category. In linked list, it will be like, okay, I am giving you a question, connect every 3 nodes together, reverse every 3 nodes, do this, do that. In that, you don't have to think anything. Answer is given to you, the end answer, how you're getting to that answer. You just have to make sure you're following the steps to what it is asking you to do. Similar, exact same thing is given to us over here. The answer is given to us, as you can see. I just have to connect the elements. So what I will do is I will take it as a linked list approach. Take it as a linked list approach. Okay, so let's see. I'm getting 1, 2, 3, 4, 5, 6, 7. Okay, not a problem. 1, 2, 3, 4, 5, 6, 7. When I'm given questions like this, I will see what I have been given in the question. I know that I cannot use Q. I know that I will be starting from root node. Okay, I know that it is a perfect binary tree. So every parent has 2 children and all the leaves are on the same level. So if every parent has 2 children, then if I find a particular node that has no left child, it means that that is the leaf node. Okay, sounds good. So what I can do is I can start connecting as I go. That is the only thing left to do. Start connecting as you traverse. So let's say I start connecting from the left hand side, means from this node to this node, this node. This I will call leftmost node. Okay, leftmost node, when I start, initially it is equal to, let's say, 1. While this is not equal to null, I will keep moving forward. So 1 is not equal to null. What I'm going to do is, whenever I am at a particular node, I will connect its children together. So I am at 1, I will say leftmost is equal to 1. So current node, let's say I start from level 1 only. So current node is also going to be equal to, let's say I say take a current node, that is also 1, because in this level I only have 1 node. So I will say so this is what is happening, right? What you have to do is, for every level you have to connect the level below it and keep moving forward in that level. So for example, for this level, when I am at 2, I will connect the children of 2 and I will then move forward to 3. And I know that the level I am currently at is already connected because the one above it did it for me. So when I'm at 1, I will be like 1 dot current dot left dot next is equal to right, current dot right. So this will be connected. Current 1 dot left dot next is equal to right, current dot right. Now it's going to be like, are there any other left in this level? No. Okay, move forward. So I will move forward and I will be like, my leftmost node is now equal to what? My current node dot left. So 2. Okay. Now I will start again. I will start from 2. I will say current node is equal to 2. In this level, this current load is equal to, for this level, the one I'm currently at. Like, okay, 2 dot left dot next is equal to 2 dot right. Connect this. After that, I will move to the another node on this level, which can be directly jumped on by current dot next, which is equal to now 3. So I will say 3. One thing I have to do is, I have to say 3. I have to connect 5 and 6 as well, right? So after I move forward, I can do one thing. Before moving forward, see, I am facing problems as I am moving forward. No brain logic is required, okay? Just do what it's asking you to do. So I'm saying, before I move forward to another level, sorry, the next node in the same level. Before I move to the next node in the same level, I have to connect this middle one also. So current, which is 2, dot right. If current dot next is not equal to null, then current dot right, which is equal to 5, dot next, which is equal to whatever it might be, is going to be equal to current, which is 2, dot next, which is equal to 3, dot left. And after that I will move current to here. Current will now be equal to 3. Similarly, it will do the same thing. It will be like current dot left is equal to current dot right. Then it's going to be like, is there anything else above it? In front of it, it's going to be like, no, it's not. Okay. Then leftmost is going to be equal to 2 dot left, which is 4. It's saying now 4 does not have a left child. I know if there's nothing here, there will be nothing here also, because it is the nature of the tree. Simple. That's it. Let me just code it, not to think about it. Okay, let's just code it. So these sorts of problems that deal with like the structure and stuff, don't think about it. No need to think, just follow the steps, and wherever you get stuck, try to see how you can get not stuck. Okay, I start with the root node. Initially, I will just say if root is equal to null, return null, not a problem. So I will say initially my leftmost node is equal to root. So I'll say node leftmost is equal to currently root. Now I will say while leftmost dot left is not equal to null. Okay, while leftmost dot left is not equal to null because of the nature of the tree, what am I going to do? I'm going to say, okay, I'm going to traverse this level. Current is going to be equal to, well, first of all, it will be leftmost. Node current is equal to leftmost. Now, while current is not equal to null, because this is automatically pointing to null, so if I'm keeping moving forward, traversing level wise, while current is not equal to null, what am I doing? I'm saying current dot left. I'm hoping you can see this pointer that I'm moving. I'll zoom in a little bit. I'm saying current dot left dot next is equal to current dot right. Current dot left dot next is equal to current dot right. After that, I will move forward to the next node in the same level. For that, I need to connect the two nodes over here, these two. So I will say if current dot next is not equal to null, I will say current dot, you're seeing what we're doing, right? We're traversing level by level, and while we're going level by level, we're connecting the level below it one by one like a chain. So before moving forward, I need to connect this bridge. So I will say before moving forward, current dot right dot next. I'm getting the linked list feeling, is equal to current dot next 3 dot left. No need to think. This is connected. After that, I will say current is equal to current dot next. Since then, this whole entire level will be over after this while loop. So after this while loop, level is over. When level is over, you go to the new level, means you start again from the leftmost. Leftmost is going to be equal to what? Leftmost is going to be equal to what? The previous leftmost's left. Previous leftmost was 2. then it will be the left of that. Leftmost is equal to previous leftmost dot left. Okay. It's asking me to return the node. Okay, just return the root node. Return the root node. It's fine. That's what it is asking. Hopefully that should work. Good question. Submit. Oh, syntax error. Sorry. Submit. Bracket error only. Yeah. Beats 100% of Java solutions, and memory is also nice. Beats 75% of some submissions. Very cool. It's a very efficient solution. Pretty nice. So yeah, root bracket like this. Easy peasy. Very simple. Okay, moving on to the next question. This was a good question. Very nice. Good question. But still easy for you because you know breadth-first search. Next question, again, the most easiest question. Nothing you have to do. This one is literally copy pasting. This was asked in Amazon and Flipkart. So if you're interested in joining Amazon or Flipkart, very easy question. From what I have seen, from what I have noticed, Amazon questions are the most easiest ones. Correct me if I'm wrong. But you can see tag has companies. So simple. You are given the binary tree, print the right side. Means if you look at the binary tree from right hand side, this is nothing. This is just level order traversal and just get the last element of every level. How simple is that? It's very simple. So when you're traversing entire level, you know we get the level size, then just get the level size, last one. That's it, last element. I'll just copy paste. Copy paste. Actually, I'll write it down, no problem. Let's say we take this one, right view. I just take this and we copy paste. It's actually very simple. I don't even have to make the diagram for this. Okay, so here list, it says list of integer. Okay, not a problem. This is all looking good. Q is added, level size is added. I don't need average. Q.poll, like I'm removing from the queue, and I'm adding in the queue as well, not a problem. If I comes to be the last element in the level, what will be the last element? I will be equal to level size minus 1 because that is the last time the loop will run. I will just add it in my result. Result.add the current node dot value. What I'm trying to not say anything negative, but is this really what kind of questions are these companies asking? It's actually like, especially in India, Amazon base pay, what is it? 12 LPA? Such unworthy questions, and people are like crazy about such companies, which is fine, but why? Like whenever I hear someone say, I'm an Amazon coding interview, I'm very scared, it's just so funny, especially in India, and like, I don't know, it's just, this is one of the mysteries I will never understand. It's very upsetting that people don't know the reality to FAANG interviews and the salary packages. But anyway, do what you like is what I always say. These questions, I don't know why you think it's difficult. Maybe something is wrong with me. But anyway, let's move forward. See, simple question. Okay, next question also very simple. Next question is saying that you're given a binary tree root only and two nodes of tree x and y, which are integers, as you can see here in the function definition. You have to return true if the nodes are cousins, otherwise false. Cousin means of the same lineage, like same level, but they should not have the common parent. Same level, but parent should not be common. Not a problem. I can just find these two nodes, and if these two, and I can find the level of these two nodes. So just find the nodes, find the level of the nodes, and find if they are siblings. That's it. So if they are not siblings and they are on the same level, then they are cousins. You can do it via breadth first search as well. You know, you can get the element like this for breadth first search, like you can get all the levels, right? But then in the level, how will you make sure that you're not taking siblings? For example, for 2 and 3, you can search in the level. Do 2 and 3 exist in the same level? Yes. But they are siblings. So how can you make sure? Actually, yeah, what you can do is, for such questions, we can make a function that just checks whether these two are siblings or not. And yeah, sibling means common parent. So cousin will be what? Cousin will be equal to level of x should be equal to level of y, and x and y should not be siblings. Okay, let's do that. Okay, here I'll paste is cousins. Right. So in order to search for this thing, this is currently given in integer. I need to get it as, I'll create a find node where I will pass root and x. Similarly, I will get the y node, root and y. I will say return. I will say the level should be same, so I can create a level method which gives me the level. I will pass root xx. The current level I'll pass 0. You know how to find the level, right? We have done this before. Should be equal to, if you're not familiar with what I'm writing right now, like what is how to find node, how to find the level, go watch the tree lecture number 1. In that I have explained this implementation in detail. So I will say root yy initial level 0. This should be true, and I will create an is sibling root xx yy. This should also not be a sibling. That's it. That's the answer. That is the answer. I will create find node first. We know how to find the node. Very simple. Tree node, find node, tree node, node, int x. So start searching from the root node. First of all, if node is equal to null, just return null. Node does not exist. If the current node that you are at, node.value is equal to x, I have found my node. These are very simple questions. These are the implementation questions we did in first video, okay? Otherwise, just call the recursion. So start searching in the left hand side. Tree node n is equal to find node, node.left. I'm searching for x. If you cannot find it, means n is equal to null. If let's say n is not equal to null, means I have found it in the left hand side of the recursion. Otherwise, try to find it in the right hand side of the recursion. Okay, fine, done. I'm not rushing into this. This we have done in lecture number 1. I'm actually explaining it again, so it's beneficial to you. So just find node, started searching from the left hand side. So currently at here, it will be like, let's say if I'm searching for 3 using this code, current node is equal to null? No, it's not. Okay. Then is it equal to 3? No, it's not. Find node dot left. Go to node dot left. Is 2 is equal to 3? No, it's not. Is it equal to is it equal to null? No, it's not. Okay. Go here. 4 equal to 3 or null? No. Go on the left hand side. 3 or null? No. Left hand side. Null? Yes. Just return null. It is returned null, so it will then check right. Null. Then it will go here. Right. Is 3 equal to null? No, it's not. Is 3 equal to 3? That is we are looking for. Yes. Return this node. Simple. You have done recursion already. You should not be scared of these things. Now, how do we find if it is a sibling or not? Boolean is sibling. Tree node, tree node x, tree node y. If node is equal to let's say null, I can say return false. Otherwise, how do we know that these are siblings? I can say node dot left is equal to x and node dot right is equal to y. Okay, so let's say you're trying to see if 2 and 3 are siblings and you're at 1. So if 1 dot left is equal to 2 and 1 dot right is equal to 3, that is one of the case. Or if that is not the case, it can also be opposite. Something like this. Node dot left is equal to y, right is equal to x. That is also another case. Or these are not siblings. It may be like you're let's say searching for 4 and 5. This is not the case at all. Then you have to apply a recursion. So or you can either find sibling in the left hand side or in the right hand side. Recursion is sibling. Now start searching for left hand side. Node dot left, x and y will remain unchanged. Or is sibling in the right hand side of the tree, x or y. That's it. Sibling done. Easy. So start from 1. Is 1 dot left equal to 2 or 3 or right? Let's say I'm searching 4 or 5. Let's say I'm searching for 4 and 5. If 4 and 5 are siblings, I'm starting from 1. Is 1 dot left equal to 4 or 5, either left or right of 1? No, it's not. Okay, then go on the left hand side. Now 2. Is either of the left and right of 2 equal to 4 or 5? Yes, it is. Okay, it will then just return true. It will return true. Okay. Now, last thing remaining, level. Int level. Initial level. If node is equal to null, what is the level? 0. If you have found the node, if node is equal to x, whatever current level is, return that. Otherwise, I can say level is equal to level, try to search it in the left hand side. And as I'm calling recursion, level will be +1. So let's say you're trying to find level for 6. Level here will be 0. You're like, okay, could not find it. I will go down. So level +1. Level here will be 1. Level here again will be 2. Found 6, return level, which is 2. So level +1. Okay. if I can say level is not equal to 0, sorry, not level, L is not equal to 0, return L. Otherwise, search in the right hand side. That's it. A program done. That should be it. Copy paste. Maybe some typo or something. Yeah, typo. Line number 23. Yeah. Line 48. I missed out on the just some typo errors. Don't worry. Commas. Submitted beats 100% of submission, so it's very efficient, time efficient. Beats more than 80% of memory also. Okay, so good solution, good scene. Okay, easy problem. More of an implementation one, so check out the first video if you are more confused. But I think just finding the level of it, I think we did this problem already. I'm not going to explain the level one. I remember I told you how to find level. Watch video number 1 in the tree playlist. Explained it in detail with all the diagram and everything. Not skipping anything. I've taught you how to do this. Okay, moving forward. There are two more questions. There's one called vertical order traversal. So here you have to add in like in this order, this vertical order. So 8 will be printed first, then this column will be printed 4, then 2 and 9, 1 and 5, then 10, 6, 3, 11, 7. Vertical order traversal. And there's another question, hard, it has a lot of thumbs up stars, called word ladder. So I realized I have to make another videos on this because this uses something we have not covered right now, which is hash maps. So we will cover hash maps and then we will cover these videos. I will make another video called advanced tree questions. Many people comment, Kunal, can you please share sliding window video? You would have done arrays. Can you make sliding window? I can, but I cannot make it before I teach you hash maps because sliding window uses hash maps. Most popular sliding window questions. So we're not skipping anything. String questions are already covered in recursion. Lot of string questions. But in hash maps, when we do hash maps, we will do string interview questions more and sliding window, 2-pointer and all these other things. Greedy and trees as well. And then, yeah. So if you already know hash maps, try it out. But if you don't, then wait for my the hash map videos. In that I will dedicate one video I will make called advanced tree questions. Okay, another question that we're doing, which is symmetric tree. This was asked in Google, Amazon, and also Apple. So Apple, so many big tech companies. Easy question, but it has a lot of thumbs up, 14,000 stars. So it is easy, but if not given to you that it's easy, you will feel like, okay, it's difficult. It's saying, given root of a binary tree, check whether it is a mirror of itself. So means if you cut it down in the middle, it should show a mirror image. So it's 1, then it's 2, 2. If it's 3, 4, then 4, 3. If it is somewhere like 1, 2, 3, it should say 3, 2, 1, something like that. So here, this is not a mirror. So even though it's saying 1, 2, 2, 3, 3, you can see it is not a mirror because here it is 3 on the right hand side, it should be left hand side, right hand side. Like a paper, if you fold it, it should be like joined together. You know what mirror means. So how do we solve this question? We know we are talking level by level, so breadth first search will be used. Every level has to be like mirror of itself. Hint number 1. See, tree questions are very simple. You just have to see the limitations you have. That is what I have done in my thought process that I explained to you. What data you are given, what you are given to work with, what is the end result, how to get there, and what all ways by which you will get stuck and how you can resolve those. Just write whenever you're given like linked list question, recursion question, tree question, just write it on pen and paper, see what you can do. See the data given to you, see the facts given to you. Those are where the answers are hidden. So we will approach this question as well. We know that level by level, every level has to be mirror as well. And we know that BFS will be used. And those are the hints that we are given. So let's see how we can use these hints to solve the problem. So when approaching tree questions, what do we know? We know that we have to start with what we have and what we know. What we know, Kunal has already taught us. When you're working level by level, use BFS. So we know BFS will be used. We know what we have. We know what we want to do. So let's try to solve it normally. We will not get the answer, but we will at least start. So that's the approach always. So you have 1, you have 2, 2, 3, 4, 4, 3. I know this is a mirror because in the middle if I cut it, I know that every level is mirror. Okay, that is fine. So every level, if I talk about level, I know I have to check this with this. I have to check this with this with this. Okay. So Q, if I'm doing level order traversal, or I will let's say add few more elements. 5, 5, 6, 6. Okay, enough. So I'm doing my Q thing. Initially I will have 1 in it. I'll say okay, 1 I know, root I don't even need to check. Root I can skip for obvious reasons. So initially I will just say I'll have let's say 2 and 3. Sorry, 2 and 2. So this one and this one, I'll be like, are these two equal? So whenever I'm checking every level, you know what I'm doing, right? We know for now that in a queue, after every level is done traversing, I know that queue will contain all the elements in the next level. So here I know that I'm checking 2 and 2. What are some of the ways via which it can be like false? So if let's say you're having 2 nodes, let's say left and right, left node and right node. If left, let's say, or right, any one is equal to null, then answer is false. That's an obvious one. If both left and right are null, then I can just skip, because it may be true that in the future, in the ahead of this level, I may have something. No, not all the left and right like this. No, we are talking about mirror. The left and right, I mean this one. This is what I meant. This is null, this is null. Okay, yeah, I got it. So we are trying to check level by level, but instead of adjacent, we will check mirrors. So we will check this one, like the end ones. So I'll start checking this one and this one. Then for the next level, I will check this with this and this with this. Then for the next level, I will check this with this, this with this, this with this, this with this. Ah, okay. That is how we can solve it. But now the problem is, how do we make sure? Because in the queue, I cannot get elements from the middle. So how do we make sure when we are checking these two, they are together, these two, they are together? Okay. How do we make sure with that? Let's see. I'm just thinking out loud, so bear with me. I don't even know how to solve this. So I'm just imagine, okay, that Kunal doesn't know how to solve this and he's given a question in interview. So far I know. So if you're given two nulls, let's say this is null, then I know I can skip it, because it may be possible that somewhere else we will have like different ones. So 2 and 2 is fine. Let's say it will be like, is 2 and 2 equal? Yes, it is. Okay. I will remove 2. I will add 3 and 4. Remove 2. Add 4 and 3. Now it's going to be like check 3 and 3, but I can't get this 3. I can only eliminate from the first. Okay, then I will not add left and right as it is. When I remove 2, I will just say what order do we need it in? We need 3, 3, 4, 4. So I will add left dot left first, then right dot right first, then left dot right, right dot left, 4, 4. Makes sense? Now you can check. 3, 3 should be same, yeah? So I will remove 3, 3, and then I will add again left dot left first, right dot right first, yeah, got it. Then left dot right first, right dot left first, 6, 6. Yeah, now we're getting it. Now we're getting it. Yeah. Okay, cool. One more thing is, previously we were skipping null, like skipping adding null in the queue. This time we will not, because you know of this case. 5, 3, 3, 8, 8. Here it will be like check null with 8. These 1 is null, so answer is false, because we need it to be symmetric. Okay, very simple. Check and then add in this order: left dot right, right dot right, left dot right, sorry, left dot left, right dot right. So add it in this order: first left of left, right of right, then left of right, and right of left. So thought process clear how I approached it. I was like, what is given to us? I know BFS will be used. I use BFS. I found myself in a problem. I need to check from corner to corner and move inside, but it was actually not storing in corner corner. So instead I use this approach to store. Now I can just code it. Okay, I will copy this. My symmetric. Okay. And here what we're going to do is it's a tree node of type integer. So I'll just copy paste. Q, Q, Q. Just do whatever we did on the whiteboard. And here I'm saying I will not add my root. I will just add first of all root of left and root of right. Q dot add root dot left, Q dot add root dot right. Please, I have explained it using multiple examples, my thought process. Work with what you are given, see the obvious things, identify the pattern, start solving it. You will get stuck, solve that stuck. How to solve tree problems. And linked list also. Okay, then I will just say check. Well, while Q is not empty, while not Q dot is empty, okay, I will add this thing left left right right left right right left after I have removed both. So once I remove, I need to store it somewhere, you know, because I'm not like, okay, remove this and then add. No, I can't add left and right. I will add left first and then right first. So while I can remove it, it's fine, but I will just store it in another node. Q dot remove pole. So now I have left and right removed. I will check now. If left and right are equal to null, either like this or this or this or this, then just skip it. Continue. If either of these are null, if let's say one is null and one is not null, then break. No, not break. Return false if any one of these is null, because you know what we are doing, right? These adjacent elements that we have in the queue are actually the mirror positions. Hope that makes sense. How are we maintaining the mirror positions? These four, the way we are adding it again inside. Okay. Another position, if these are not equal, if let's say we say left dot val is not equal to right dot value, then also it is not mirror. If none of these return false, return true, but we have to add as well. Now add left left right right. So q dot add left dot left, right dot right, left dot right, right dot left. Should be very simple to understand. Oh, by the way, this is node, so it won't have generics here, because Q is giving me node only, tree node type, so I can just store it here. Should look fine. Let me copy paste and submit. Oh, it added 2 semicolons. I'm very bad at typos. Looks good. Accepted. Easy to understand, simple stuff. Right? Cool. What is the time complexity? O of n, because we are traversing every node only once. And we are using Q, so space complexity is also O of n. Okay, that was it. Okay, so that was breadth first search. We did some nice questions, and now any question that is given to you that uses breadth first search, you'll be able to do it. Okay, second topic, also the most important. It's probably more important than BFS. Can't really compare, but like both are important, but this one has more interesting questions, if you will. And this one is called depth first search, opposite of breadth first search. Breadth first search, you're level by level. Depth first search is top to bottom. Let's get started. So there are many ways by which you can do traversal up to down, which is depth first, and we've already done this in the past. So if you see the first video of the binary search trees, I believe we have done this already. We have done 3 types of such traversals: pre-order, in-order, and post-order. So pre-order traversal, we know we have something like AB. Pre-order traversal is plus, then A, then B. In-order traversal, it is first A, then plus, then B, means left and right. If you don't want to talk about A and B, you can talk about left and right. Left, right, left, right, left, right, and then post order means first left, then right, then node. So what is the meaning of this thing? What do you mean by traversing like this? It's pretty simple. Basically means that we are first going to, if we talk about, let's say, pre-order traversal, which is this one, we are first going to visit the root node, for example, and then we are going to visit all the left trees and then all the right trees recursively. We have done this in the past. Okay, so it's all about the ways in which you are exploring the tree. So here we're saying node first, then left and then right. So if I talk about a tree, let's say we talk about a tree and I say simple tree like we have 10 over here, then I have 12 or 20. Taking the same example I did in the last questions, doesn't matter. Not a binary search tree, but a normal binary tree. Now in order traversal for this, sorry, not in order, preorder. Is going to be what? Preorder is first node, then left and then right. First the node itself like root, then left and then right tree. Okay. So here I will start from root 10, I will print 10, then I will go on left. Now before going to left or right, I will print 20, then I will go to left again. Print 15, then I will go to left. It's null. Okay, back to 15, right? Nothing. Okay, back to 15, back to 20. So 20 is printed. 20's entire left is printed. Now 20 is right, which is 13. Okay, then 13 left, right, nothing. Okay, then I go back. 20 is printed, left is printed, right is printed. Then 10. 10 is already printed at first. Then all the left of 10 is printed. Then right of 10. Make sense? That's pre-order traversal. So this is the left tree. This is the right tree. For every single tree, you can also follow the same pattern. You can see the same pattern. Node root will be printed first, then left tree and then right tree. Okay. Sounds good? That is pre-order traversal. Okay. Similarly, in order, we have done this before as well. In order traversal. So whenever you need to visit the root first. So when to use pre-order traversal? When you have to visit the do something at that level and then move down, use a pre-order traversal. Do something at that level, then move down, then use pre-order. Okay. Now in order. In order will be what? In order means first left, then the current node, like the root of it, then right. So I will not print 10, I will go in the left. I will not print 20, I will go in the left. Then I will go in the left, it is what? Null. I will come back. Left entirely and left tree I have already gone through. Now I will print 15. After that I will be like, okay, print what? Print the node. So 15 means left hand side has been printed. So I will then print the node itself, so 20. And then the right hand side 13. Sounds good? Then 12, sorry, then 10 and then 12. So you can see root will be printed later, left tree, right tree. Make sense? If you're still unaware, then I would recommend checking out the first lecture. Now, when do you use in-order traversal? You know, in in-order, we are going to leftmost first. Leftmost first. So when to use it? In a binary search tree, when you want lowest value. So when you want lower value, in that case, use it. So you're traversing, see, all the left hand side, then you're traversing right hand side. Okay, so if you need to find any element that is smaller than the root node, you have to work with that, then use in-order traversal. Now post-order, again very simple. Post-order, you will print the left tree first, right tree after that, and then the node. Okay, so post order. It is going to be what? Left tree first. So 10, no, it will not print. 20, it will not print. 15, left, yeah, 15, it will print. Then it will go back and it will print right. So left, right first, then node. 15, 13, 20. So it will be like 15, 13, 20. Okay. After that, let's say if I consider this node, left tree is printed 15, 13, 20. Right tree will be printed after that, so 12. And after that, this node 12, and then the node itself, which was 10. So you can see left first, right after that, root after that. This is important if you have to perform some functions on the root at the last. For example, if you want to delete the tree, then you will try to delete all the left child first, all the right after that, and then you will delete the root node. Why? Because if you delete the root node at the very first, then these will be pointers will be lost. So there will be like memory wastage. These will still be available. There will be no way to reach it. Memory leak will be there. Understand? Make sense? So for example, when you want to delete a tree, you use post order. When you delete a tree, then you use post order. So whenever you want to work with the root node at the last, then you use post order. These are three ways, and we have written the code for this already. So don't have to worry about that right now. We'll obviously write the code again and again. But yeah, I've done the code in the previous sections. You can check it out. Let's directly jump on to some questions and see how it works. Okay, so let's take a look at some questions. The first one is a most popular one when we learn about depth first search. So whenever in a question you're asked to like go down from up to down or whatever, or bottom to up or whatever, we will look at depth first search. So here it's saying find the diameter of a binary tree. This was asked in Google and Amazon and Facebook. It's an easy question but very popular. So you are given root of binary tree, return the length of the diameter of the tree. Diameter of the binary tree is the length of the longest part between any two nodes in the tree. May or may not pass from the root node. Okay, this 5213 is one path, 425 is one path. Okay, 4213 is one part. What is the size of 4213? 4. 5213 is 4. 213 is another path. So between any two nodes in the tree, you can have. So the hint that we are getting over here is we are learning about things, we are going about things in this question from up to down or down to up or whatever. So we know that depth first search will be used. Okay, so let's look at the approach and how to approach this problem. So if I take an example for a tree, let's say I'll just make some tree example, make 1, 2, 3, something like this. One tree over here, one more over here, one more, and can have other things like one more. Okay, not a problem. What is the diameter of this tree? Diameter is the tree maximum path between two nodes. So 1, 2, 3, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's 1. 8 is the answer for 1. What other path you can have? You can have 1, 2, 3, 4, 5, 6, 7, 8. Let's say I have one more. 9. No. Yeah, that's another path you can have. Yeah. Hold on, let me just erase this. Okay, so one of the paths you can have is like this. That is 1, 2, 3, 4, 5, 6, 7, 8. Other you can have is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the blue path is the longest one. So you know the diameter, as you can see in this question, it may not pass through the root node. So the diameter in this case is what? The blue path. And the diameter is what? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the diameter. So how do we figure this out? It's very simple, just simple recursion again. I will just say simple recursion that let's say I have a diameter over here. Diameter initially, 0. Then I can say that I will just start from my root node. Again, try to see where you will start from, what things you are already given. So I will say for every node, I will calculate the height of the left tree and the right tree. Then I will have one of the diameters that passes through that node. Is it not true? So I will say, okay, give me the height of the left tree, give me the height of the right tree. It's going to be like, okay, height of the left tree and right tree, I can get it to you. And the diameter is going to be equal to what? We have already learned the method for calculating the height. So I want to, but I will not explain here because I've already covered it. Video number 1, calculating the height of the tree. If you still want, I can do it, no problem at all. So let's say I'm starting from the root node. So to calculate the height of a tree, what I'm going to do is for a node, I'll start from the main node, for example. I'll say calculate the height of the left and right. So it will go again in the left, then it will go again in the left, then it will go again in the left. It'll say null, this will be 0. Then it will go right, right, right. This will be 0. And then it will be returning 0. This will return 0. So 0 plus 0 plus 1 for that node. So this will be height 1. Now it will, left hand side will return 0. Left hand side will return 1. Right hand side will return 0. So what is the maximum of left and right? Maximum left and right is 1. 1 plus 1, 2. This is height 2 of this node. Similarly for this node, maximum of 2 and 0 plus 1. See, because it is taking these two plus 1, because it's taking this one in itself also. Makes sense for every node. So it will be like 2 plus 1. This will be height 3. Similarly, it will be like maximum of 3 comma. This is height what? 1, 2, 3, 4. 4, which is 4. So this is height 5. Okay. No, actually, this is 1, 2, 3. Height 2, 3. So 1, 2, 1, 2, 3, 4. So this is height of this is 1, 2, 3. This is also 3. 3 plus 3. Sorry, 3 or 3, which is bigger. 3 is only fine. So it's 4. This side is 4. Make sense? Cool. So we know how to calculate the height. But what we're going to do is at every node, we will also calculate the diameter. We'll also calculate the diameter. So diameter for this one will be equal to what? This 3, 1. At this point, let's say I'm at this point, diameter will be equal to left height. This height is 0 plus right height, which is 2 plus 1. So diameter is what? 3, if you will. Okay. So the height of left tree plus right tree plus 1. That is the diameter. Actually, I did one little mistake because we're doing left plus right, left comma right is the maximum plus 1. So in reality this would also be 1. It will not be 0. 1, 1. This will become 2. This is null, so it will be 0. 3, 4, 4, 5. Okay? Make sense? Cool. So that's how you're calculating diameter for every, and then you will keep updating the maximum number of diameter, which is a, let's say, a global keyword, we are like a global variable we are taking. We will keep updating it. So it will basically calculate the diameter for every single node, and yeah, basically about it. What will be the time complexity of this? You can notice that every single node is only getting visited once. And since we're doing left first, then right first, then the current node. Isn't that what we're doing? Left first, then right first, then the current node. Are you understanding? I think so. If not, we will code it, don't worry. So this is what? Left, right first. This is post order. Okay? So simple, very easy. And we're visiting every node once. So it will be O of n, and recursion will take O of n. Let me try to code this, and then maybe it will be easy for you to understand. Then I'll walk through it again, and then you will see. Okay, so here we have diameter of tree, and what I'm going to do is I'm going to take a int diameter initially equal to 0, and here I'm just going to say return the diameter, but I will keep updating the diameter in another function, and that would be, let's say, height of, let's say, root. I will create int height tree node. Okay, now if the node becomes null, just return 0. If node is equal to null, return 0. Otherwise, what I'm doing is, think about the recursion. I'm saying get the height of left node, right node, plus 1 will be the height of here. So I'll say int left height is equal to height of node dot left, right height is equal to height of node dot right. This is why we use recursion, it makes things easier. So the height will be equal to what? Of this node, the current node I am at will be equal to what? Math dot max of left height, right height plus 1. That's it. So height for this will be null 0 0 plus 1 1. Height of this will be 0 and 1, maximum is 1, plus 1 2. Height of this will be 3. Height of this will be 1 and 3, which is maximum. 3 is maximum plus 1. You see how the recursion is working? Easy. But what we have to do is, when for every node you have calculated height for left and right, calculate diameter also. That is the diameter. What is the maximum height of left and right? Plus 1, like this red line I just showed you. And I will just update the overall diameter. Okay, and also here in the question, it's saying it's the length of the longest part. So our question currently, if you check, it's giving me like the number of nodes. So edges will be like the total, like if it's 4, so answer should be 3, which is the length of the path. So I'll just say diameter minus 1. Submit, should be fine. Accepted beats 100% and memory beats 98%, so very fast, very efficient, and very simple. Okay, so it'll start from, if I want to talk about this one, 1 2 3 4 5. 1 2 3 4 5. 4 5. It will be like, I will calculate this later, first give me the answer of left. 2 will be like, later give me answer of left. 4 will be like, later give me answer of left. Left giving 0, right giving 0, this will be height 1. Then it will be like, okay, left given, I will take the answer later, give me answer from right first. Right will be like also 1, this will be like what? Okay, I am okay, so like this is 1, this is 1. So here, as you can say, it's saying left height I got, right height I got. Then it will just be like equal to, it will return 2. So this will be equal to 2. But before returning, it will be like diameter. So diameter will be equal to left height plus right height plus 1. So for this, it will be equal to 1 plus 1 plus 1. And actually, when it's done doing both the ones. So if I'm talking about this one over here, after doing left and right, it will take diameter. Diameter will be what? Left height plus right height plus 1, which is 1 plus 1 plus 1, which is 3. So here it will say 3. Okay, for 2. Then we'll go outside. It will come outside from here for 1. Then we'll calculate for right hand side, which is for right height. This will be 1. Then we'll like left plus right plus 1 is the diameter, which is 2 plus 1 plus 1, 4. So overall diameter is changed to 4. And then it will update its height as 2, 1, which is maximum 2, plus 1, 3. And then in the end, it will return not 4, because I don't want the number of nodes. I want, so it will return 4 minus 1, which is equal to 3. That is my answer. 3 is the length of the path. Make sense? I've already told you how to put debug pointer and debug as well. So you can do that also, but very simple. Time, space, complexity, clear. It's very easy. Okay, let's move forward. So as you can see in the previous example, we're like, okay, we will get the left height first, right height first, and then we will work with the root node. Isn't that what we are doing? So what is that kind of traversal? Post order. Post order traversal we did. So we'll like get the left first answer, left tree, then get the right tree, and then the main tree. So that is how you have to figure out in order, pre-order or post-order, which type of traversal is being used in the answer that we want. That is the key to solving depth first search problems. Okay, this next question is a bit funny one. There's this guy Max Howell. He's the creator of Homebrew, the package manager for macOS, MacBooks, and such a popular tool being used by millions of people around the world. I use it. If you have a Mac, you use it. And he actually gave an interview at Google, and he was rejected because he could not invert a binary tree. If Max had seen my DSA playlist, he would see that it's pretty easy. But this is not a comment on Max. I personally believe that, yeah, there should be some interviews that focus only on your projects and open source rather than such questions like invert a binary tree, reverse a linked list, or whatever. I think as a programmer, this does not really define you, which is why I am on Max's side on this one. But anyway, you are preparing for FAANG, fine, no problem. You have to learn how to solve these problems. Inverting a binary tree, one of the most easiest question and one of the most popular questions. It is so easy, I don't even want to do it. So what I want you to do is, see, when I see easy, when I'm seeing, because I'm not able to see a hard question that was used at Google or Facebook or Amazon or Apple. I can't. I've been making this video now, I'm recording it right now. It's been a few more hours to go, and I am bored because none of these questions are worth my time, and these should not be worth your time as well. Similarly, these companies are also not worth my time. So whenever my friend is like, oh, I am applying for Amazon, Google in India, very upset and very stressed about the interview. Interviews are like, this is the level of interview. Why are you scared? This is a funny interview. These are the sort of questions they ask. Okay, you will also reach my level once when you have practiced data structures algorithms, and then you will realize how easy it is to clear these interviews. There's nothing that these companies can ask you if you're going for a software engineering role from lead code that you would not be able to do if you're done the right preparation. So invert a binary tree, very popular question, and on lead code it's easy question. I don't know where this world is headed. Anyway, so invert a binary tree. How do we invert the binary tree? It's saying this is a tree. Let's take a look. And if I want to invert it, then it's saying that swap the nodes. So I swapped this to 2 and 7 swapped, and these two swapped. See? Swapped. Okay. It's very simple. I'm going up to down, so I know depth first search will be used. Now, which one will be used? Pre-order, in-order, post-order. So I can imagine, I can say that from every node, what is the easiest thing I can do? I can swap the left and right child. That is the easiest thing I can do. So imagine I am at 4 and I have swapped 2 and 7. That is fine. Then I have to make sure that the subtrees are already swapped. So if I'm at 4 and I'm swapping 2 and 7, I have to make sure that the 2 and 7 internally, the 1, 3 and 6, 9, internally these two are swapped as well. So what is this? Again, post order. Swap the left ones first, right ones first, and 4 will be like, after that I will swap. Oh, what a joke. What a joke. Not worth our time, such questions. Exactly same approach like we did in the previous one. Post order. You understand, right? Would it make sense for me to draw the diagram again and again for everything? I can do it if you want. But same thing we did over here. Left height, right height, +1. Similarly, left swap, right swap, and then the main swap. Oh. So simple. So I can literally, I can read this when you see on the screen. So if I take this example, the 1 2 3 4 5 1, this one. So here I can literally speak the code when I'm looking at the screen. So it will start root is equal to null, then return null. So if I'm here, it will return null. And then left is equal to what? Invert tree left, right is equal to invert tree right. That is the node that we are getting. So this will just return the left node. This will just return the right node because there is no swapping involved here. And then when left and right has returned, then it will swap. And then return 2 will return itself from where it was called. So it will swap. Okay. If I write it clearly, it will swap. And then it will return from it was called. So it will be like, okay, left is swapped, now right will be swapped. There is nothing, so 3 will remain 3. Or if I add it like 8, 9, 3 will be like, okay, I will swap myself later. 8 and 9, swap these two first. Okay, not a problem. Now 3 will be like, okay, left is done, right is done. I've swapped these as well. Now I will return. So it will be returned from where it was called. So it was called from the main one. Main one will be like, okay, left is swapped, right is swapped. Now I will swap these two. So it will be like 1, 3, 2, 5, 4, 9, 8. So you see the internals are already swapped. How easy was that? It is so simple, literally 3-4 lines of code. Nothing to do. Dry run done. Okay, copy this. Public tree node. Okay, what a weird question. Just so easy. This is getting too easy for you. We have to find new challenges in life. When I was preparing for FAANG, I was like, life is going too easy. I need some challenges in life. This is too easy for me. So I was like, okay, let's contribute to open source. There are big projects, very complex code base. Takes a while to understand. Preparing for FAANG, it's one of the easiest things you can do. Take 2 hours every morning, done. Okay. Return null. Then what I will do is, okay, so I am at, let's say 4, it will be like, hey, I will swap 2 and 7, that is fine, but before that swap the internal nodes. Okay, tree node left will be equal to invert tree root dot left. So it will return the right node only, left and right node only, but after swapping. So after it has left and right, it will be like just swap left and right. Root dot left is equal to right, and root dot right is equal to left. In the end, just return root. Do you want to see a dry run of this again? I will show a dry run, because then you complain. Oh Kunal, maybe it's easy for you, it's difficult for us. You have done an entire playlist on recursion. What are you talking about? Entire playlist I have done on recursion. This is a basic question. Beats 100% Java users. Very efficient solution. If I remove the main check, 1, 2, 3, 4, 5 lines of code. What is this? Just 5, 1, 2, 3, 4, 5, 6 lines of code. That's it. Google interview question, one of the most popular invert binary tree question. This is why you should not give up in the hype. Or reverse a linked list, popular question, difficult. Invert a binary tree, homebrew creator could not do it. Difficult question, Google, big tech company. No. Joke. Always remember, if you're preparing for FAANG, questions will be easy. If you want difficult interviews, apply to startups. Okay. So easy. Want to do dry run? Let's do dry run. So I will start doing the dry run on my iPad. Okay. 4271369. 4271369. This is the reason I told you tree is one of the funniest interview preparation topics, because questions are a joke. So where's the code? Yeah, here's the code right here. If root is equal to null, just take a look at this code, okay? Left, right, and then swap. Okay. So it's going to be like, this is the original tree that I have. Okay, never mind. I'll draw another one. 2, 7, 1, 3, 6, 9. Code says start from the root node. Okay, start from here. Is 4 equal to null? No, it's not. Okay, go on the left hand side. I'll go on the left hand side here. Is 2 equal to null? No, it's not. Go on the left hand side again. Is 1 equal to null? No, it's not. Go on the left hand side again. So you can even draw the recursion stack. 4, then 2, then 1. Now 1 will go on the left hand side. It is null. Yeah, return null. Right hand side, it is null, return null. So both null are returned, and it will swap null, which is fine, and then it will return itself. It is returning itself. Isn't that what it's doing? Can't believe I'm teaching you basic recursion, because there are some people. Return root, passing root. So this is always the current node we are working with. It is returning itself. So it will return 1. 1 will come out of the function stack. So this has returned 1. Now 2 is like, okay, left I have gotten 1. I can assume that all the children of left are also reversed. Now it will be like, okay, 3, it is your turn. 3 will be do the same thing. 3 will go over here, left and right, null, null, swap. 3 will be returned also. 3 will be returned also. Now 2 will be like, I'm in my 2 function stack. Please watch a recursion playlist. This 2 means I'm in the 2. I'm working with 2 right now. 2 will be like, okay, left I have, right I have. 1 and 3, I will swap these. Okay, swap it. Swap it. 3, 1. Swapped, and after that return root means return 2. 2 will come out of the function stack. See, I'm explaining you in detail every single thing. 2 will come out of the function stack. So 2 is swapped. Whenever something comes out function stack, I know that its tree is internally, what are the subtrees were, they are already reversed. Now 4 will be like, okay, I have come out of line 29 here. This line 29. Now it will call the right tree. For the right tree, 7 will go inside. Then 6 will go inside. 6 will be swapped, it will be removed. Then 9 will go inside. 9 will be swapped. Then 7 will be like, okay, 6 and 9 I have, swap it. So 9 here, 6 here. Same thing as it happened in the left hand side. 9 here, 6 here. 7 will be like, okay, done, return root. 7 will be returned. 7 will come out of the function stack. Now 4 will be like, okay, 2 and 7, I have to swap. So it will swap 2 and 7, and you can see we will get this thing. This thing. Second one. 2 and 7 swapped. So internally also swapped. Okay. 2 and 7 swap. 4, 7, 2. Internally it's already swapped. 9, 6, 3, 1. Is this not the mirror? Yeah. Done. 4 will come out of the function stack. Returned from where it was called, which was what? Main. Function stack over, program over. Easy. Okay. Now, what is the time complexity? O of n, because n number of nodes and we are only visiting it once. Space complexity is what? Because we are using recursion. So what is the maximum number of items that we can have in recursion at once? We know that when it's calling left or right, this is actually, I have mentioned, I think 100 times in the recursion playlist, that the maximum height of the recursion stack is always equal to the height of the recursion tree. Okay, so height of the tree. So for example, this will refresh your memory. At no point of time, any two nodes, means more than one node at the same level, will be in the recursion tree at once. Hence, the maximum height of the recursion tree, maximum number of calls in the recursion tree at once will be the height of recursion, height of the original tree. So space complexity is O of h or O of log n, because that is the height of the tree. Please study, get serious. These things I've covered already, but I'm still explaining again. Anyway, move forward. Next question. Okay, next is another question from Google. Maximum depth of binary tree, thumbs up. The way I find questions for you people is I see the companies it were asked before and the ones that have the most thumbs up on lead code. So I just make a list. I also add these to the assignments, so you can check out the link, GitHub link in the description below. So all the assignments. Given the root of the binary tree, return a maximum depth. Okay, a binary tree's maximum depth is the number of nodes along the longest path from the root node to the leaf node. I am not doing this question. I am now getting frustrated. This is a Google question. And so many thumbs up. What is happening? We have to do some good level questions, otherwise I will go mad. I am not doing this question. This is too easy. Okay, I can literally speak the code. Maximum depth is the number of nodes along the longest path from the root node to the leaf node. Okay, from the root to the leaf, maximum path. I will assume again post order. I will assume left has the most one or right has the most one. Take the maximum and do +1. Simple. Try to code it on your own. Pause this video and code it on your own. But if not, then I can do it. No problem. It won't take long. Okay, I hope you tried it, but I believe this is one of the easiest questions. I don't know why I put this over here. It's actually a waste of time. It's our waste of time that we're doing this question, but still, I'll do it very easily, like very fast, okay? Because it's a waste of time, so you know we've done better questions like this. So yeah, again, we did the height one, right? The diameter, similar to that. So I'll be like, if root is equal to null, then just return 0. Then it will be like, okay, number of nodes. So maximum nodes, I say, okay, get the number of, like get the depth for the left hand one and the right hand one. Okay, left is equal to what? Max depth for the left and max depth for the right. Then what is the, so I have gotten left and I have gotten right. Then for the node that I'm currently at, so see post order, left first, right first, then for the current node. Now for the node I'm currently at, what is the depth? Math.max of left comma right +1, and I will just return that for that answer. Similarly, it will return for this answer, it will return in the end this answer. Recursion, we don't want to spend much time on this. Submitted, beats 100% of Java users. Very simple question. Okay, moving forward. Alright, next question by Facebook. Again, too many thumbs up. Convert sorted array to binary search tree. Oh, okay, good question. Easy question. We have done AVL trees before, so you can do it with that, but that's fine. But there's a simpler way to do this. I'm not going to solve this question because I solved it throughout in the very first video of trees. So if you remember, if you don't remember, go watch right now. I created a function or a method called from sorted array. So we took mid and we did all those things. I explained it clearly in that, and I did all the diagrams and everything, dry run of the code as well, debugging, examples, walkthrough, everything, code running, convert array to binary search. Yeah, and sorted array to binary search tree. Yeah, we did this. Lecture number 1. Watch it. I'm not going to do this one. Okay, moving on. Alright, next question I found on LeetCode and also from a previous company. Facebook, now called Meta. Now we have done the, I'm not doing any more easy questions, otherwise I will lose my mind. Okay, doesn't matter which company they were asked in. Easy questions are not worth your time now. We have seen the binary search, binary tree easy questions. They're just a joke. So we are going to move up a little bit. Let's do some medium questions. So medium question, 11,000 thumbs up, very good, asked in Facebook. Nice, this will be fun. Now my energy is back up. So let's see. Given the root of the binary tree, flatten the tree into a linked list. Okay, binary tree is given. You have to convert that into a linked list or a skewed binary tree. You see this one? So it's just converting the structure into this. Many ways to do it, pre-order, in-order, post-order, but it is asking me to convert it in pre-order traversal. What is pre-order? If I'm at the root node, I will do things at root node first. Then I will go in the left and then I will go in the right. Isn't that what pre-order is? Right? If you see over here in my iPad, pre-order, do the things at root node first. Don't be like, okay, give me left, give me the answer, right, give me the answer, then I will do it. No, that is post-order. We've done some questions on that already. Pre-order here it's saying root node, I'm at one particular node, I will solve it on that node and then I will solve downwards. Meaning, when you're solving the problem on that node, it may be possible that the down will not already be fixed. Okay, solving left first, right first, and then I'm doing the current node. It means what? Down, left and right are already fixed. Now fix the current node. Okay, solving current node first, then left and right means the current level is solved. After that, I will go down and solve left and right. In order, left node right means left subtree is solved, then I will solve with the current node whatever I have, and then I will solve the right part. Most of the time you use what do you use? Most of the time that I have seen, post order, but it obviously depends on the question. So I already again many times I'm explaining you the thought process, how to pick the approach. So when you're given this question, okay, I have to convert it into a skewed tree. It's saying in pre-order traversal. Okay, so whenever you're given questions like this in big tech companies, try to come up with the bad solution first. Tell them the time complexity, space complexity, and then they will ask you, okay, can you optimize it? And then do a little drama and be like, oh yeah, I can optimize it like this. So let me tell you the bad solution first, and then we will try to optimize it. So bad solution. This is a good question. I will just take the lead code example only. It's a good example. So Facebook. If you know depth first search, you know that it's saying pre-order traversal, so we know depth first search is being used. So half problem is solved. Now, how to actually do this thing? So you are given 1, 2, 5, 3, 4, 6. Approach number 1 is normal pre-order 2. It's very simple. It's saying do pre-order traversal and create a tree. So what you can do is normal pre-order traversal. Normal pre-order traversal. As you traverse, store nodes in a queue so that I can use the first in first out. In the end, remove from queue one by one and make linked list. Simple solution. We are doing what it is asking us to do. Inorder traversal, okay, no problem, I will do inorder traversal. Inorder traversal will be 1. Inorder means what? Node, then left, then right. So node means I am at 1. Yeah, I will work with 1 first, then I will go in the left. 2, I will work with 2 first, then I will go in left. 3, I will then go 4, then I will go to 5. Yeah, I will plus 5, then 6. So 1, 2, 3, 4, 5, 6. Okay, I will store this in a queue, and when the traversal is over, I will take items one by one out of queue. If I take 1 out of the queue, I will put 1 over here. 1 dot left, I will just say null. Right, I will say is equal to the next item in the queue, which is 2. 2 dot left will be null. Next item will be the next item in the queue, which is 3. So on and so forth, it will be done. So space and time complexity both is O of n, because I'm traversing every element 1, time complexity n, and queue will be storing n elements, so O of n. Can we do it in O of 1 space? O of 1 space. Okay. So what type of question is this? Linked list type question. For the 100th time I am asking you, forget everything, I am asking you one thing for the 100th time. Do you give any importance to thinking when it comes to such structural linked list, especially linked list based question? It is asking me to do something, it is telling me how to do it. Is there any logic involved over here? That is my main question. Because if you say yes, then you will overcomplicate your thinking and you will go downhill in your interview preparation. Have you seen the linked list questions video I did? I am not thinking for 1 second in that video. Swap every 3 nodes, reverse the linked list, do this, do that, merge every 3 linked list or whatever. It is telling me what to do, so I am just making the diagram and solving it. I am making the arrows. Whatever the arrow is saying, I am writing that in code. Anyone who tries to tell you that you need to think about this or whatever is teaching you in the wrong way. This is not how you solve such questions. The reason you don't have to think is because there is nothing to think. So outside data structures algorithms, in general life also, places in which it is not required to think and you're thinking, it means you're wasting your time. Okay. For example, any luck-based game. If you like winning a lottery or something, you like pick a random number and we will see if you win the lottery or not. If you're thinking which number to pick, they're giving you 5 numbers: 4,800, 9,200, 7,600, 2,100, 6,539, and you have spent 1 hour thinking which number to pick. That is a situation in life where thinking is not required, but you are wasting your time in thinking. Such questions are those type of problems. You don't have to think here. Everything is given to you. Don't think. Just do what the interviewer is asking you, or in this case, the question is asking you. Okay, so let's see how to do this. Okay, so what I'm going to do is I'm going to write the tree again. It's saying 1. Anyone who says think about this, do that is misguiding you. Don't trust that, because you will overcomplicate things. Okay, I will not think. I will just see what the question is asking me. No thinking. Question is saying I have to make a linked list. Okay, no problem. So I will have to swap somewhere, and it's saying it should be in the same order as a pre-order traversal. Pre-order traversal. Okay, meaning I am at this node right now. I will work with this node first. So it has a left and right. I will have to work with left and right. So meaning I have to fix this first before I go down. That is pre-order traversal. How do I fix this? Fixing it basically means the left hand child has to go away. The left should become null. Doesn't matter if the below subtrees are solved or not. I do not care. Okay, I do not care. All I care about is how do I make the left child of 1 equal to null? Right. And I know left is going to come at first over here. So I know that left is coming after the node. That is what pre-order is, right? Node, left, right. So if I'm making a list, it's saying it should be node, left, right order. So try to print it. We've already tried printing it. Here you go, 1, 2, 3, 4, 5, 6. So right hand side should have 2. So somehow I have to do this. The right hand side should have 2. Somehow. But then it also had something else on the right hand side, which was 5 and 6. Where would 5 and 6 go? Ideally. See what the question is saying. 5 and 6 will go over here. I know that. No thinking required. How did I know it will go over here? How did I know that? It's actually, I don't even know. I'm just trying to think. Then I will solve the left and then I will solve the right. But before solving that, I have to solve node. For node, I know that I have to put this in the right hand side, but right may already have something. Oh, then I will put it somewhere in the left tree. Obviously, it will go in the left tree, 5 and 6, somewhere in the left tree, where there is no right element. Okay. Alright, where there is no right element. Can I do undo in this? Never mind, can't do undo, never mind. So what I'm saying is 1, 2, 3, 4, 5, 6. So before moving it, 1, 2, 3, 1, 2, 5, 3, 4, 6. 1, 2, 5, 3, 4, 6. So before moving 2 on the left hand, 2 on the right hand side of 1, I have to move this 5, 6 somewhere. This 5, 6 I'm going to move towards in the left tree somewhere. But where? In the left tree, wherever I find the first empty space where there is no right child. 2 has a right child. the rightmost, I will put it on the rightmost because I'm already making stuff right. So I want to put all the things on the right. That's what I'm doing. Left should only be, left is not meant for removal of things. Left should always be null. So never in my any case I will put anything in left. I will only put stuff in right. So 2, what is the rightmost empty, so that's the thing you're looking for. Rightmost empty space in the left subtree. Rightmost is this one. So I will put it over here. 5 and 6. And then I will move the entire tree from left to right. There we go. Now same thing I will do for 2. So now I'm at 2. Now I am at 2. For 2 it's going to be like, okay, fix 2 first. Meaning 3 should come over here. So if 3 should come over here, this entire thing will go on the left tree where the first right element is empty. So here in this null I will put 4, 3, 5, 6. Sorry, 4, 5, 6. And then this entire thing I will put on this side. 3, 4, 5, 6. Oh, very easy. And then I will go over here. No change required. No change required, no change required, none. Solve. Question done. Okay, very simple. Very easy. What is the theorem that we came up with? I'm not going to write it down. I'm going to dictate it. Check if the node that you're currently at, check if it has a left child. And if there's a left child, then find the rightmost element for it. And do the rightmost elements is equal to current node dot right. Okay, right child of current node, that's what we did. And then the left child, just convert that into right child. That's it. Every node you're visiting once, O of n, but you're not taking extra space, so time complexity constant. I did a trial run already. I did a dry run, showed you how it works. So I'm going to code it now. And hopefully that should be, I told you 2 approaches. There are multiple approaches you can use, even more worse you can use, but I think this is the best one that you should tell the interviewer. Okay, let's code it. Okay, I'm going to copy this, paste it here, and just follow the diagram. That's it. Follow the diagram. I will first start from root node. So I will say if root is equal to null, I will say return null. Okay, so I will start from there, and I will say that I have to change my root. It's saying change the root itself because tree node root. So there's nothing to return. Okay, no problem. So while root is not equal to null, no, I will not change root. Root will remain the same. I have to change the structure of root. So tree node, I will say current is equal to root, and while current is not equal to null. So it's pretty simple object-oriented programming. I don't have to change root itself. So what I'm going to do is look at the diagram. I know that I'm here at 1. I need to find the rightmost empty element on the left hand subtree. So rightmost empty element on left hand subtree, which is if I have a left hand subtree, if current dot left is not equal to null, then only I can find the rightmost left tree. So in this left tree, I have to find the rightmost empty element, so I can put this over here. Rightmost empty element, I will say temp is equal to, let's say I start from left, and I will say while temp dot right is not equal to null, just keep going right. So it'll be like, is 4 equal to null? No, so it's going to be over here, temp is equal to current dot left. So means 2. Is 2 dot right equal to null? No. Then temp is equal to 2 dot right, which is 4. Now is 4 dot right equal to null? Yes, it is. It will come out of the while loop. Come out of the while loop. So means I am here at 4 now. So I need to put this thing at 4's right. So I will say, see, I'm just doing what the diagram is telling me. Okay, this is how you take the approach to, this is how I was clear to, I was able to clear all my coding interviews of like Google and stuff. They don't ask you such questions that often because these are implementation based questions, but these are often asked in QA rounds. So don't think too much, just do whatever the diagram is telling you to do. So current dot right I will put over here at last dot right. So here at my last of the right, which is my temp, dot right is going to be equal to what? Current dot right. So meaning this entire thing is now here. Okay, now I need to put this thing over here. So current's right will be equal to the left. And then current dot left will be equal to what? Null. See, all these are null. Null. Current dot left will be null. Current dot left null. After that, I am, let's say now here my current will move forward also to fix the other trees. How do we move forward? Current is equal to now current dot right. Current dot right. We are able to solve these questions very easily because we are not directly jumping on the question, we are jumping on the thought process. We submit this. Oh, no return type, right? There should be no return type because it's not asking for any return type. Always be sure when you're copy pasting. Submitted. Beats 100% of Java runtime and 96.71% in memory because constant space complexity. What was I doing returning null to a void? I need some sleep. But anyway, you get the idea. Simple, good question, Facebook question, easy question. Okay, move forward. Next question. All right, so next question. This was asked in Amazon and Google. Medium question, very too many thumbs up. It says medium, but it's actually easy. It's actually just like 3-4 lines of solution, very easy. It's saying you're given a binary tree. You have to tell whether it is binary search tree or not. You know what a binary search tree is? For every node on the left hand side, all have to be smaller than it. On the right hand side, all have to be larger than it. Many approach to do it, pre-order, in order, whatever you want to do. Let's do pre-order. We will check for that node whether it is fine with left and right child, and then we will check for its children. That's it, very simple. Okay, so here we're going to check. Let's say I have a valid binary search tree. Let me make a valid binary search tree. So I have 5 over here, and then I have, let's say, 4, 10, should only have less than this, or I can put 3 here. No, I will put 4 here, and I will put, let's say, 2 here, and let's say I put 6 here, then I will have 5 here. This will contain 8, this will contain 20 something, 31, no problem. So we are starting, what do we know? We are starting from root node. We can take it however approach we want. We will first check whether this condition is satisfied, and then we will check for left tree and right tree. So that is pre-order traversal, no problem. You can do in order also if you want. So I will check it for what? How do we know? we need to look back. So for 4, let's say for example, I'm just thinking out loud. For 4, I need to look back that I know 4 should be less than 6, and for 10, I know that 10 should be more than 6. So when I'm at the lower recursion calls, how do we get the data from the previous call, which is this one? Similarly, for 2, I need the data of 4. For 5, we need the data of 4. Maybe I can make a helper function and I can pass it in the recursion calls. Initially, that value can be null. I can take an integer, wrapper class, capital integer, and I can just compare it with that. Okay, so initially, let's say it's null. Low and high, for example. Okay, so the low and high we can say currently it's null and null. So this will be like, okay, true, because both are null. Then we go down. So if I go down, then low will not change. As you can see, low will not change. For 4, low will remain null only, but high will change 6. There should be no element greater than 6 over here. Lower, it can go as much lower as it wants, right? So that is why no limit. For this also, it can go as much low as it wants, but the higher limit will be 4. For this 5, it can not go as low as it wants. The lowest it can go is 4 and the highest it can go is 6. Okay, so that's it. Do the check, and when you're going down, if you're going on the left hand side, then low is not changing but high is changing to node dot value, and if you're going on the right hand side, then high is not changing. As you can see, 6 did not change, but low is changed to node dot value. Okay, done. That's it. So after that, you go over here and you check whether 4 is less than 6. Okay, node dot value should be, if it is less than equal to whatever we have, then yeah, it will give you the error. So for example, let's say we have 9 here. So it'll be like, hey, is the node dot value like greater than equal to high? It should not be. Then return false. Otherwise, keep moving forward. Very simple. Let me code this really quick. Okay, what is the space and time complexity? Recursion O of n, visiting every node 1, time complexity O of n, space complexity O of n. Okay, so good question, not bad, but still not that, I'm not happy with it that much. Valid binary search tree, I'll just call another one called helper. I will pass the root and I will just part null and null. So I will say public boolean helper function, zoom in a little bit, hide the files. So you can see clearly now. Okay. Tree node, integer low, it should not go lower than this. I will show dry run also again, so don't worry. Right. If node is equal to null, that means return true. Okay, it is binary tree, no problem. Good. Binary search tree. Now I will say, I will check for the level I am at right now. If my node dot value becomes less than the lower amount that is asked, then means it is false. If if node dot value becomes greater than equal to high, then also return false. You are at a node value, that node value has some limit set, you're going over that. So, but since This is of type like wrapper class, so I will say if this is not equal to null, because if it is null then there is no limit. You can do whatever you want. If low is not equal to null, and if high is not equal to null, and after this I will go on left and right. Return left should be true, right should be true. So I will say boolean left tree is equal to boolean, I will do the right tree as well. Both should be balanced. So I will say helper, I will say node dot left. When you're going in left, low is not changing, but there is a upper limit. Upper limit is now being set to the current node dot value. Helper, now low will be current node dot value, node dot right current node dot value, high will not change, and these both should be true. Left tree and right tree both should be true. Copy paste, submit. Again 100% faster than all submissions, so good. Very fast, very easy, simple. Dry run is very easy. Currently is 6 null, no it's not. I'll be like these two things will not be taking place because both are null. After that left tree, as you can see, this is the condition. Similarly it will keep fulfilling the conditions like this. This condition will be no upper limit, lower limit 6, lower limit 6, upper limit 10, so on and so forth. If it never returns false, it will keep returning true. And so true, 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 true. Easy. Okay, so very easy. We discussed space and time complexity also. It's very simple. This sort of recursion we've already done multiple times. This is a pre-order, and well, technically we're also doing like after we're getting, yeah, that's fine, yeah, it's good. Computing at the current level, then doing left and right tree. The next question asked in Amazon, lowest common ancestor of a binary tree. Let's take a look. Lowest common ancestor. What is lowest common ancestor? Definition on Wikipedia. You're saying find the lowest common ancestor of two given nodes in a tree. Okay, two nodes are given. Oh, thank God it's given in the node type tree node. It's good. I don't have to find nodes then. Sometimes they give it in numbers, then you have to search and do whatever. But anyway, the lowest common ancestor is defined between two nodes P and Q as the lowest node in the tree that has both P and Q as descendants, where we allow a node to be a descendant of itself. Okay. And I have given 5 and 1. 5 and 1. Lowest common ancestor will be 3. Yeah, that's true. 3. Example number 2, it's saying 5 and 4. 5 and 4, lowest common ancestor will be 5, because a node can be an ancestor of itself. It's very easy. 2 and 0 will be what? What is the lowest common node that both 2 and 0 are children of, or grandchildren of, or whatever? 3. So you know we are going up to down or something. So depth first search. Hint given, 50% solution. Done. So we know DFS will be used. So that's it. DFS will be used. So how do we approach this? Thought process. Think about it. Pause this video. Try to do it yourself. Then I will tell you. Okay, so let's take a look at this question. It's actually very easy now because 50% question is solved. I can see from the pattern that, depth first search will be used. So let's try that. Let's say I am doing the same tree. How will we use depth first search? So my iPad here, 3, 5, 1. I will not rush, I will tell you my thought process. For now, my thought process is I know depth first search will be used. That I know because that's the way we are going. We are going down. So depth first search. Okay, this is fine. And here I can see that I am given, let's say, node 5, 8, for example. So what I'm going to do is I'm going to use again, let's say we use, so one thing is that we will try to find the answer as soon as possible, closer to the root. We will try to find the answer as soon as possible, closer to the root. That is why we use preorder. First try to see if the answer is there. If it is not, go on left and go on right. So I am at 3. I will check for 3. I will check. How do we know? Is 3 equal to either 5 or 8? If it is, then that's the answer. It can't go more above than that. No, it's not. It is not. So I will go in the left hand side. So I'm here now. Is 5 equal to either 5 or 8? Oh yes, it is. Then the left hand side answer of this is going to be equal to 5. This is going to return 5. No. Yeah, it is going to return 5. That yeah, you found 5 over here. Then I'll go on the right hand side, and in the right hand side it will be like is 1 equal to either 5 or 8? No, it's not. Okay, then go on the left hand side. Go on the left hand side. 0 is nothing, it will return null. This is going to return null, nothing. Then right hand side 8, yeah, 8 is fine, so it will return 8. So we know that we have found the item in both the left and right of this node. It means that the answer is what? This node. Okay, so if let's say the current node you are at, if node is equal to, if let's say this is P and Q, P or Q, then return that node. Okay, so example 5 means, okay, 5 is equal to the node that we are searching for. Hence, I will not go down. I will end my call here. Return the node. Okay. Then otherwise, go left, then go right. After left and right, if you get something, if let's say left and right not equal to null, it means the answer is this current node that you are at. Current node that you are at. Okay. But there can be an example. Let's say if I'm talking about 5, 4, for example, okay, I'm going to erase it, but the video is being recorded, so you can watch it again. I'm going to remove this. After this is going to be like go in the right hand side after it has found 5. So it found 5. Now it will go on the right hand side. Okay, so it has found something in the left. Now 4 may not lie here in the right hand side of 3. So it will be like, okay, yeah, it does not lie. So it will return null. This will return null. So I have gotten left is something and right is equal to null. It only means that the other element 4 lies in the area where we are not allowed to look at, because it doesn't make sense. It will not change my answer because 5 is coming first. It only means that my 4 will lie in the, I can assure you it will lie in the subtree of 5 that I have already found. No need to look for it. 5 is the answer. So if left is equal to null, right is equal to the answer. Otherwise, left is equal to the answer. All the cases covered. If you found both left and right, it means that node is the answer because it has found left also, right also. And since we are searching from the top, we are not directly jumping onto the leaf nodes. It means we are making sure we are going in ascending order of the distance. So the first one we found will be the lowest common ancestor. So you see how I approached this problem. Started with best first search because I knew that the catch here was ignoring once you have found the element. That was the little bit of a hint that you need to do yourself. But the thought process of that was same. Like, it's pretty obvious. Like, okay, found an element. Then if I have found something and something lies below it, then I know that itself is the answer because lowest common ancestor can be itself. So no point in searching below. Okay, let's code it. So this is the little theorem or formula. Copy paste. Paste it over here. If root is equal to null, just return null. The example we saw where the right hand side was giving null. Otherwise I will check if node is equal to p or q. So if this root, if root is equal to p or root is equal to q, means I have found one of the nodes. I will just say return root. I have found one of these. No need to go down, just return from here. Otherwise go down. Tree node left is equal to lowest common ancestor, root dot left p comma q, lowest common ancestor right is equal to root dot right p comma q. Now I have gotten my answer from right and left. If left and right is not equal to null, it means that I have found one item in the left, one item in the right. So this current node that I am at, that is the answer. Left is not equal to null. I hope you're able to understand my thought process, how I started the journey. Return root. Otherwise I can say if left is equal to null, return right, otherwise return left. This I can use the operator. If left is equal to null, if this is true, return right, otherwise return left. It's very simple. We have done this format before. Copy paste, submit, should work. 98% faster, 89% memory faster. Okay, we are visiting every node once, so O of n, and the stack itself will take O of n. Will it take O of n? What do you think? Will it take O of n, or what is it going to take? As you can see over here, either left or right. It will take O of height of tree. O of log n is space, and O of n is time complexity. Okay, let's move forward. Next question. By the way, all of these code samples and everything, the links you can find in the description below, and you can run it on your browser itself, very easy. Next question. Kth smallest element in a binary search tree. Again, 10,000 likes, very popular question. This question, company, which company is what it was asked in? Facebook, Amazon and Google. But again, easy question. Kth smallest element in binary search tree. Given the root of the binary search tree and integer k, return kth smallest value. It's a binary search tree. Okay, binary search tree, not just binary tree. Return the kth smallest value of all the values of the nodes in the tree. Kth smallest. Kth smallest. Okay. So this is the first smallest number. First smallest is 1 only. Okay. Third smallest number is 3. Okay. Kth smallest number. So one way via which you can do this is, it is saying it's a binary search tree. So if you go and do in-order traversal, so like in-order traversal. So you'll go 1, then 2, then 3, 4, 5, 6. So you do in-order traversal, it will give you sorted array. And then just take the kth item from that array. You can do that. That is easy. Are you able to understand what I'm saying? In-order traversal, just do that. Let me show you. Okay, so at the beginning of this video only I told you, when you're trying to find lowest numbers, you will do in-order traversal. Go skip to the videos first. You will see when I was telling you, right, about not the first of the video, but first part of the depth first search. And I was telling about the 3 traversal algorithms, pre, in, and post. I also told you when to use which one. For that, in the in-order one, I told you, you will use it when you're trying to find smallest items. So 5, 6, 3. So that's another hint, another 50% question solved. You know in-order will be used. Now the idea is how to use it. See, I'm telling you thought process also. How did I know in-order will be used? You can either store it in an array, just do an entire in-order traversal. You know how to do in-order traversal. I will not tell you that. I've done this multiple times. Store it in an array, take the kth item. But we will try not to store it in array because already we are doing recursion tree. So in-order traversal I need to do. Okay, I will keep doing in-order traversal. In-order means left first, then the current node, then right. So it will go left, it will go left, it will go left, it will go left, it will return null. Then if it's returning null, after that it will check for 1. Okay, it is checking for this 1. So 1 is the first smallest item I have found. So I can take a global counter. Initially count will be 0. Initially count will be 0. So first I have returned this, like it will be null. So count will be over here equal to, count will be equal to 1. I will be like, is count equal to k, which is equal to, let's say, 3. No, it's not. So okay, go on the right hand side. Right hand side is nothing. Then it will return null. Then both right and left over, so it will be over. I'll be like, okay, left has returned me null. So I will do count plus plus. This is like the second smallest element I have found. Then I will check, is 2 equal to 3? No, we want third smallest. You are giving me second smallest. Okay, then after that, right hand side null, return null, go back, it'll come out of here, and then it will be like counter 3. So like, is 3 equal to 3? Yes, it is. I have found my answer. So now I will not call right hand side or anything. I will just return 3. So it will keep returning 3 above, it will return 3. Okay. I will not also do count plus plus or anything else. So that's it. That's the solution. Okay. So call left first because we're doing in order. So left, then current level node, whatever you're doing, then right. Then you check. If left is not equal to null, then my answer is what? Just return left, means I have found my answer. So for example, in 5, it is left is returned. So you're like, oh, answer already found in the below somewhere. Don't do anything, just return left. 5 will also return left, which is 3. 3 is the answer. Return left means you have found something down there. So just return left. Otherwise, count plus plus. Hope you're able to understand how I was able to do that. Kunal, how did you know you have to go to the leftmost? Because I know in order will be used, because I know smallest item we have to find. Count plus plus. And then what? If count is equal to k, just return the node you are currently at. Otherwise, call in the right. Simple. Done. That's it. Easy. Okay. Similar space and time complexity like we done in previous questions so often for this time complexity here. So I'm gonna code this. Okay, the main doubt here is how did you know left you have to go? Because I know, because I told you the 3 cases. And I know we need to find element lowest. It's a binary search tree. So we can do in order traversal. Left first. Before that, if root is equal to base condition, left first, left is equal to kth smallest root dot left comma k. Left done. If left is not equal to null means I have found my answer somewhere below. Then just return I found my answer. Otherwise do count plus plus. Take a count here. Then if count becomes equal to k, then just return the node. Then this root is the answer. Otherwise, right hand side. Otherwise, the answer will be somewhere in right hand side. One thing is that it's, as you can see, little copy paste, like little mistake. It's asking integer, but we are doing actually type tree node. See, we're returning the node itself. So I can call this helper, helper, helper. And I can have the kth smallest here. Return helper root k dot val. Submit. Oh, tree node, not node, tree node. Okay, beats 100% of Java solutions, and memory wise also 99.89%. So very, very cool. Very easy problem. Okay, I multiple times explained to you how I approach this. How did I know I have to go left hand side? Because it's asking me left hand side, sorry, smaller elements. So I will go in order. Whenever it asks you smaller, and in binary search tree, one more tip, in binary search tree, if it's asking for ordered, like an order sorted order, do in order traversal, because in order traversal gives you sorted order of a binary search tree. Okay, let's move forward. Okay, let's move forward. Next, we have a popular question from Amazon. So it's asked in Amazon many times. Question is simple. It says you are given pre-order and in-order traversal of the binary tree. You have to make a tree from it. Okay. For example, this one, pre-order is given to us 3, 9, 20, 15, 7. 3, 9, 20, 15, 7, and in order is given. In order is what? 9, 3. Okay, this is given. So with pre-order, since we've already done this, let me show you. I was actually writing it down. Yeah, so pre-order, if you see, if we go on the above, see preorder, it is root node. The first element is the root node, as you can see 10 over here. In order, it is left, root and right. So I know the root node, I know this is the left, this is the right. Okay. So preorder is node, root, left or right. I know this is left, I know this is right. Now again, for what I can do is, I can just call recursion. So for this recursive subtree, this can be another preorder, in order. So similarly, now the root for this will be equal to 20. Makes sense? Easy? Very easy. So I need to find this index. I know the first index 0, but then I need to find where 3 lies in the in order. So a simple for loop should be fine. Then I can call in the recursion tree and it will build my tree. Let's see how we will do this. So the recursion for this is, again, so the thing is, you may have realized by now the questions that are like implementation based questions, you don't have to think much. Just see what the data is given and work with it. So let's say first I try to create, I know the 3 will be over here. So I'll make 3 as a root node and then I will call recursion. So left hand part is going to be equal to the recursion call. For the left hand part, this is the recursion call, which is going to contain what? Pre and in. The pre is going to be equal to this thing and the in order will also be equal to this thing. So 9, 9. For the right hand side, preorder will be equal to 20, 15, 7 and in order will be equal to 15, 27. So instead of calling recursion, this is actually the same thing. Then it will do same thing over here. It will pick this, put this as root, then call the same two ones similarly. Easy? Sounds good? So if this index that I have over here, I call this index, then how do we determine where this thing is cutting? That is very easy. We know that it first starts with left. So however element I have on the left hand side of this thing, index, which is 1, that is how many I will take on the right hand side of this thing. So only 1 9 is here, so only 1 9 I will take. So I will slice the index from 1 to whatever index this I am at plus 1 because it's exclusive. Make sense? For example, if it was something like 8, 9. How do I know this is left? I know this is left because it's on the left hand side of the index that I have found. So how much from the third, from this thing, the root node, how many times I have to go in the right hand side to get my left tree? Only twice because this length is twice. This twice is equal to from index number 1 till whatever this thing is. This thing is what? Till index plus 1 because 1 is already, it's so easy. So 1 I have already taken from here. I need to go 2 in order, which is index. So I will go index times faster. Index is position 3. So I'm going here in position 3. if it is inclusive. If it is exclusive means if it is not taking the index value, then +1. So index values I will write 0, 1, 2, 3, 4, 5. So I need to take from index number 1 till index number 3. That is what I need. 3 being exclusive. So it will be 0, 1, 2. 2 is equal to actually index. I need 3, hence index +1. Oh, okay. Now you should understand. It's very simple. And all the remaining ones, whatever is remaining is from what? From index +1, which is 2 + 1, 3. So from index +1 till the end. So this thing left is equal to 1 till index +1. Right is equal to index +1 till the end. Okay, cool, simple. That I will just call the recursion on it. And it will keep building the tree for me. Okay, let's do that. So I'm going to copy this. Important question asked many times. I have seen this question, very popular. I will say that if the length is 0, return null. My root node is going to be equal to 0th element. Okay. My index initially, let's say, is 0. Now I have to find this index in Inorder traversal. Zoom in a little bit so you can see. I is equal to 0, I is less than Inorder dot length I plus plus. I will say if Inorder of I is equal to my root, I have found the index. Okay, I will create a node with root. Okay, node created. So I made this node. Now recursion. Node.left is same thing again with this condition. Node.right is same thing with this array. Build tree. I need a copy of this thing. So I can take arrays.copy of range. We have done arrays before, so you can check out the arrays lecture. Arrays.copy of range. Pre or preorder array from 1 till index +1. And the second argument, which is Inorder array. Inorder array is what? From 0 till index. 0 till index. Zero till index. Node.left done. Easy. Node.right similarly. Node.right is equal to what? Now node.right is for preorder it is index +1 till end. Preorder it is index +1 till end. Oh no, end what? A preorder dot length. And for this it is index +1 till end. and is again inorder.length. That will be done. It will then just return the node. Okay, that's it. That should build my tree. See, it was very simple. I told you. Submit. Hopefully no errors. Preorder. Simple rookie mistake. Oh, tree node. I took it as node. Tree node. No, new tree node. New tree. I'll get error again. New tree node. Checking. Now it's submitted. Cool. Good enough. Okay. So even though it's accepting, I think we are using arrays.copy of range. That's why it's giving me too much time. Kunal, how to solve this? That I can't tell you right now because you have not done hash maps, but this can be solved using hash maps. So remember I told you I will make one video, advanced tree questions. I will tell you in that one. But yeah, for now it's good. Yeah, similarly you can do tree using post order and in order also. That you can try yourself now. It's very simple. So yeah, very cool. Okay, so now moving forward to the next question. This is a hard one. A lot of thumbs up, so I wanted to do this one. And very popular. It was asked in Google, Facebook, and Amazon. It is actually not a hard question. It is a very simple question. Okay, it's not hard at all. It is literally an easy level category question. So it's saying serialize and deserialize your binary tree. Serialize basically means I will convert this and put it in a file. Deserialize means I will convert that file and put it back in the tree form. So initially you can see it is giving a tree node and it's saying serialize it means convert it into a string. So you have to convert it into a string. Okay, sounds good. So you can either do in order, pre-order, post order, whatever you want. But there are some things to think about. So you convert that in a string. Otherwise and then when you take the string, you can convert from the string, you can make the tree again, like the tree data structure, whole structure. That is like deserialization. So serialization is converting into a string or something else like data. Deserialization is doing the opposite. It is saying string, but I will do a list of strings, okay, just to make things easier. But you can convert it in strings. I've done a dedicated video on string buffer builder, whatever. You can try it out. Just to make things simpler, I will explain it to you. But there are two ways to do this. Okay, two ways to do this. Let's see. Okay, two ways to do it. Let's say we all know we have to. So thought process is very simple. We know we have to convert it into a list of something. Let's say array. Okay, no problem at all. So we can just traverse this and put it in an array, and then we have to put it back. Not a problem. So I will be like, okay, just taking the example what is given to me already. 1, 2, 3. I am telling you thought process also. Okay, for now I am a very clueless person, so I am just going with the flow, and we will see how it goes. So I will convert it into, let's say I do in order. Okay, I do in order. So in order I will start from here, then 2, then it will be 1, then it will be again in order will be, then it will be 4, 3, 5. That is in order. Not a problem. My question to you is, if you are given an in order traversal like this, or in the previous example we did, in order and pre-order was given, using these two we were able to make a tree. But my question to you is, if you're only given in order, one traversal, or if you're only given pre-order, or if you're only given post-order, can you make the tree? That is the question. Can you make the tree or not? Let's say if the tree was something like this, or let's say I put 4 over here, remove 5. Okay, The problem will lie over here that you may not know where nulls are lying, the null values. I can put 5 over here again, that's fine. But I hope you understand the problem, why we were given pre-order and in order, not just one pre-order, one in order, because then you will not know where null is lying. You will not know that. It can either be like this or like this. You may not know. Okay, so for example, I know this is in order, right? I know that is in order. I know this is root node. How do I know if it's very simple. How do I know if this is left and this is right, or if this 3 is left and this 1 is right, or if this 1 is left and these 3 are right? How do I know that? You can't know that. So one way via which you can solve this is have pre and in order stored. That is how you can serialize it. That is way number 1. You have pre-order and in order stored, and that is how you can serialize it. Simple. But that is the problem, is that you're using two ways. You're storing it in 2 ways, one additional extra. We don't want to do that. We want to be cool, efficient. So instead what we'll do is only store pre-order or in order, whatever you want. Only store that. Let's say we only store pre-order, but we will also store the null. Null, 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 null. Store pre-order with null. What is going to be the pre-order with null? Let's say I store pre-order with null. So it will be 1. Pre-order is what? Node, root, left, right. 2 will come here, 2. Again left. So null. Nothing on the other sides. This will also be null. Then 3 will be printed. 3 will be here. 4 will be here. Null, null. 5 will be here. Null, null. That is pre-order traversal. Hope that is correct. Okay, so that's it. That's my serialization. I can store it in a list, but the question on LeetCode asks me to store it in a string. So you can store it in a string also. Now how do I use this and create our tree back? I will take this. I will create a new node, 1, right? As you can see over here. And I will check if there is null value, then I will just return null. So I will say my node dot left is equal to, just pass the stream whatever is remaining. So I will say okay, 2 is here, removed, 2 will added. Left is again equal to whatever is taken out of the stream, what is remaining. So I took out 1, I took out 2, now I took out null, so it will be null and it will not go other side. Now it will call right hand side. Right hand side will be again what is removed, null. Then it will be like okay, both are done. Then if both left and right are done, just return this particular node. Just be returned from where it was called. It was called from this first node dot left. Now it will call node dot right, which will be whatever is removed, 3 will be removed. Now it will call node dot left, whatever is removed, 4 is removed. Now it will call 4 dot left, whatever is removed, this is removed, null. So it will not call anything, it will return. Now 4 dot right, again what is removed, null is removed, null. Nothing, left and right both done, removed. So return 4 will be returned. if 4 is returned, 3 left hand side is done, 3 dot right it will say whatever is removed, 5. Then 5 dot left, whatever is removed, null. 5 dot right, whatever is removed, null. Both are removed, return 5. 3 left and right both are returned, return 3. 1, 2 and 3 both are returned, return 1 from where it was called, main. Oh, very simple, easy, cool. Okay, sounds good. Let's code this. What is the space complexity, time complexity? Time complexity O of n. But since I'm going breadth wise, maximum height O of h, which is height of the tree, log n, that is the space complexity. Okay. There's actually a better way to do this using heaps, but we don't know heaps right now. When we do up heap, down heap in the heap next lectures, I will tell you how heaps use the array to create such trees. So directly you can jump onto parent and child using formulas. Very simple, I will tell you when we do heaps. We will do it completely from scratch. It's the basic thing in heap, like how to form heaps. It's the most basic thing, so don't worry, you won't skip it, it will be the first lecture only. One thing I want to mention over here is that since I'm removing item from the first element, if I'm doing that from list, it will like remove the first element, then it will shift all the ones on the left hand side, remove another, shift on the left hand side. So instead I can just remove from the last, but then I will have to reverse this entire thing. So I will do that. I hope that is clear. If I remove 1, then it will shift all, 2, shift all, 3. So I don't want to do that. I will reverse it once, O of n, and then constant time I will remove from the back. So it will be same thing, but I will be removing from back, but it will be fine because I've reversed it. I will actually, create a new class. Serialize, deserialize, dot Java. Okay, good question, hard question. I think it's hard based on the implementation only, but other than that, it's pretty straightforward question. Like we haven't done anything that is new over here. So public, what? I will create a list of string serialize. What is the spelling? Serialize? Is that it? Maybe. Okay. Node, and I will create a helper function. I will say void serialize, no, helper function node list of string of my strings. Okay, here I'm going to say I'm going to create a list of string, call it list is equal to new array list. What I'm going to do is I'm going to call my helper function with my node and my list, and it's going to then return the list because I have passed the list reference variable. Any change I made in the helper function will change the original list. Basic object-oriented programming, that's why. Now helper function I am converting into a list. So if node is equal to null, I will say just add null, so I can add in a string. So I can say, I can just call it list dot add null, return. Otherwise I can say list dot add, convert this node dot value into string. Okay, then I will just call recursion helper node dot left list helper node dot right list. Very easy. just calling recursion, then that's it. But this is the main part now. Here I'm going to say node deserialize. I'm giving it a list of string. This will be my list. So using this list of string, you have to deserialize it. If you want to store it in a string like the question asks, this is a good homework for you. A hint I can give you is after every number store a comma, then you can split it across the comma. Easy. That you can do. So I will reverse it because I don't want to do the swap thing again and again. And I will say my node is equal to helper 2 of my, here I'll pass my list, return node. I'll create my helper, node helper list of string list. Now what do? I get the value. First of all, value is equal to what? List dot remove from the last item. Last is what? List dot size -1. So I have gotten the first item, for example, it will be here. So I have gotten that, and I will create a node out of it. So I will say node is equal to new node, convert it into an integer because it's a string, integer dot parseInt the value. But what if it is null? If value dot char at 0 is equal to, or if string dot equals whatever you want to do is equal to n, means it's null, and it is null. Otherwise, create this node and call left and right. Node dot left is equal to helper 2 of list. Node dot right is equal to helper 2 of list. In the end, just return node. It's exactly the same thing I did over here. I showed you the whole dry run. That's the same thing that is happening. So your homework is try to convert this list of string into string and submit on LeetCode. And a hint is you can add in comma so that you can separate. Rest everything is same. Moving on to another series of questions. We are not done yet. When I told you, you only need to watch this one video in order to solve tree problems, I meant it. Code can be found in the description. If you haven't already, then like, share, subscribe, share with your friends, take a screenshot or whatever you want to do, share your learnings, write a blog, give a shout out on socials, share with your friend. If you love the course, please, I want to hear it on socials, because it's not for me, it's for other people, so that they can discover the course for free. Tree is the most important topic, and I'm trying so hard to make it easy for you to look at a question, you will be like, oh, I know how to solve it. Okay, moving forward, some more questions we'll do because those are important topics. Tree only, DFS only, and these are asked quite a lot, so let's do that. Okay, next question, path sum. This is an easy one, and by that you can assume that it was asked in Amazon, because from what we have seen, most easy questions are being asked in Amazon. Not a personal comment, but just what I have observed. So easy question asked in Amazon, and very simple. You're given a target sum, and in the tree you have to find a root to leaf path that all the sum of those nodes are going to be equal to the target sum. So here target sum 22 is given to you. So you know 5 plus 4 plus 11 plus 2 gives you 22. There are hard versions of this path sum as well, like maximum path sum, something that is not like, let's say, all the path sum, so it's not necessarily from the root till the leaf only. But this is an easy one, and it's an Amazon question, so we will do this. Then we will do serious questions. This question is a joke. So pause this video, think about it. 50% of the question is solved. It's not 50, 80% question is solved because you know we are going top to bottom. So you know depth first search will be used. So let's just use depth first search. Okay, this is my tree, Amazon. 5, 4, 8, 11. There might be any possible scenario that you'll be like, Kunal, what if there are multiple solutions? Yes, we will do that question also. Don't worry. There may be multiple paths that lead to the sum of one number. That is a hard question. Not really hard, it's easy, but we are doing the easy one first. Okay, so this is the one that is given to me. Now, how are we going to solve this? It's very simple. I know things that I already know. Breadth first search will be used. So I know I will start from here. Sum is equal to, let's say, 22. So I know we have to take the, initially, let's say I am starting from the root node. So I'm starting from here. Sum required here is 22. Okay, or I'll just put it over here, 22. 22 is required. 22 is required and I have 5 over here. So if I take this 5 node, then how much would be required? 22 minus 5, 17. So if I go over here, it says 17 is required, 17 is required. I will first go on the left hand side. So I am doing again what? Current node, check current node, then left and right. So I am doing a pre-order traversal again, 17. So I'm like 4 and 17. I can take 4, then 13 will be required. I will go on the left hand side again. Then I can go on the left hand side again. 2 will be required. Now I am on the leaf. It's like you require 2 and I have 7 to give. Hence, this is not a valid path. Go back. Now I will try here. It says again 2 is required. 2 is required and I am giving you 2. I have found the answer. I will return true from here. So this will return false. This will return true. Either true or false. One has to be true. One path I need. I will return left or right. So false or true gives me true. I will return true. True. Got the answer. Right may return something or not. Right will return false. I got 2. False on true, true. Will return true. Very simple. I will not waste much time on this because this is a joke. But yeah, very easy question. Okay. Sounds good. Height of tree, space complexity, O of n, time complexity. Let's code this. So here I have my method, copy paste. Simple question. DFS. I'll maybe create a new file called pathsum.java. This is where I will put all the path sum questions. Okay, this is the simplest one. Zoom in a little bit so you can see. So here I have, it says root and target sum. So I will say if root is equal to null, this will be return false. Then I can say if the current node that I am at, if that is a leaf node and its sum is equal to, and its value is equal to the sum. If root dot value is equal to the sum and root dot left is equal to null and root dot right is also equal to null. So if it is a leaf node and the leaf node's value is equal to the sum that is left for me, means I have found my answer. Otherwise, do recursion. Otherwise, see if left has the answer or right has the answer. Return has path sum, root dot left, sum remaining will be minus root dot value, okay, minus sum minus root dot value, 22 minus 5, 17 will be passed down, or I can get the answer from right hand side, root dot right, sum minus root dot value. Yeah, that's it. Easy question. Submit. Oh, it says target sum. Okay, I'll just put sum here. Yeah, that's okay. 100% solution. I'll put sum here, not a problem. Okay, next question. This is medium. Medium question. What is the question? Question says that sum root to leaf numbers. Since we know this is a medium question, I know it was not asked in Amazon, 100%. I know it might be asked, it may be asked in like Microsoft or Apple, yeah, and Google. This is why there are so many influencers from Amazon, because it's like this you can get into Amazon. But I would like to say by this you can get into any FAANG company, not just Amazon. Yeah, this is not a personal opinion. You already know by seeing all these questions and the solutions that it's very easy. Okay, sum root to leaf numbers. What is this? Let's see. Zooming in a little bit. You are given the root of a binary tree containing digits from 0 to 9 only. Okay, that is good. Each root to leaf path in the tree represents a number. Return the total sum of all the root to leaf paths. Okay. So root to leaf path. One path is 495, 491 and 40. 495 plus 491 plus 40 gives 1026. Okay, that is the question. Okay. 60% question is solved because I'm going top to down. So I know Kunal told us this is depth. So depth first search. Depth first search will be used. Let's start. I don't know how to solve this. So I will start with depth first search and I hope I develop the answer. This is what you have to do in interviews also. Whatever hint you're getting, try solving problem. Speak out loud because they have to see your problem solving abilities. And then you will find the answer just like I find the answers. Thought process, intuition. Let's move forward. I would highly recommend, this is also easy question only. I would highly recommend pausing the video and trying it yourself before you see my solution. But let's move forward. Path sum numbers, whatever it's called. 490. I'll turn on my iPad. Yeah. So 49051. Okay. So what I'm going to do is I'm going to think what happens and what is given to me in the, I'm only given root node. So I can create a helper function that will have the path sum. Okay. Like till that level. So for example, I start with 0 and what do? How do I make it into numbers? 495, 491, 40. How do I do that? So when I'm at root node, I can calculate the path as, let's say, sorry, the sum, the number till there. Okay, the number till there. I can say the number here is equal to what? whatever sum I have, let's say if I have 0 here, so it should be 4. Here it should be 49. Here it should be 495. Okay, multiplied by 10. Okay, see, it's getting multiplied by 10. 10 into 0 plus 4, which is equal to 4. Now 4 is here. Here I have 4. This will be previous one. So 4 into 10 plus 9, which is 49. Yeah, this is 49 till here. This one will be 49 into 10. Oh, very easy. Plus 5, which is, this is 495. And when you hit the leaf node, it means you have found your answer. So you can just return 495. This will return 495. Plus, then you go on the right hand side. This will be 491, hit leaf node. Yeah. So it will return 495 plus 491. Whatever that might be. Then it will go back. This will be equal to what? 495 plus 491 back. Now this will be calling in the left hand side. 4 into 10 plus 0, 40. This is 40, so it will return 40. This will be 40 plus whatever you got from the left hand side. From left hand side you got 495 plus 491 plus 40. That is your answer. Oh yeah, fun, solved, good. That was easy. That was good. So I told you the dry run thought process, easy. Just started with breadth first search, and I kept maintaining the path till that level, but I will only take it when I reach the root. Okay. So I will keep putting it down. And you know how to put this down. If I need 49, I need to pass it down here. It is very easy. Pass it in the argument, recursion playlist, very easy. We have been doing this multiple times in this video. Let's code this. Gain time complexity is same as previous ones, very easy question. Nice. So here, some numbers, root node, I will say return helper root and 0. Okay. So if it is null, then just return 0. Otherwise, what is the path sum till that node? The previous one into 10 plus the current. So sum is equal to the previous one, which is sum into 10 plus current. So node dot value. After that, just call left plus right. Helper of node dot left sum plus, so this is the sum how we are passing it down. Helper of node dot right sum. But if you reach the leaf node, then just return that. No need to call below if you reach the leaf node, and if that is the answer. So if node dot left is equal to null and node dot right is equal to null, return sum. So yeah, 4 will be returned, 491 will be returned. This will get left and right, it will return the sum. Yeah, very good, easy. I showed you the dry run also, debugging also, I showed you everything. Copy, paste, submit. Good, 100% faster and very fast, 0 millisecond, very good. Good question, still not as good as I want it to be. Still, these are boring questions. Let's do another one. By the way, the space complexity here, in the worst case, will be O of n. In case, it's like the height is, it's like not a balanced tree. But yeah, time complexity O of n, not a problem, which is pretty fast. And yeah. So take a look at the next question. Hard, 15,000 thumbs up. Binary tree maximum path sum. Asked in Facebook, this question is a joke. It's not a hard question, it's copy pasting the previous question. It's a very easy question. What is the question? A path in a binary tree is a sequence of nodes which adjacent nodes. Yeah, I know that. And a node can only appear in the sequence. I know that. Maximum path sum. So 2, 1, 3 is one path. This is another path. 15, 27. Any path it can take. Okay. Well, it's easy for me, might be overwhelming to you if you don't know the previous questions that we did. So yeah, credit where credit is due. It's an okay question. I still wouldn't be happy about solving it. To me, it's easy, but fine. You people are learning, so it's okay. Confusions you may have is, oh, so many paths, so many combinations exist. How do we find the optimal path? Maximum path. So this 15, 27 can be one. 9 minus 10, 20, 15, that can be one. 9 minus 10, 27 can be one. Right? So many options. So you have to find the maximum. I know that we are talking about path, so like up to down or whatever. So I know DFS will be used. So let's say 30% question is solved. But how do we find the maximum? Do I find all the paths and take the maximum? That's not very efficient. Yeah, that's one way you can do it. It's not very efficient. Okay, so first of all, I take my words back. This is not a good question. It's a good question, but it's very easy. I don't think this should be hard here. It should be easy question here. It's very simple. You can solve it if you pause it. We have done this before. It's post-order traversal. We have done such things before. It's very simple. For every node, we will traverse every node once. That is fine. For every node, we will see what is the maximum value of the path that we can get with this node in it. So if I take minus 10, what is the maximum path I can get with having minus 10 in it? So what is the maximum of left plus maximum possible of right plus minus 10? Similarly, possible, you get the idea, right? And then we will maintain a global maximum. Oh, it's similar to that other global maximum thing we did. We had a global variable for maximum, something we did with diameter or whatever. Same thing is happening over here. Calculate for left, calculate for right, then include it in the, include the current value with path. Are you able to understand? I don't think you are. But anyway, let's bring the whiteboard. That will make you understand. So it's very simple. It's an easy question because we did this before. Minus 10, 9, 20, 15, 7. So for every node, I know depth first search, so I will start from here. For every node, I will compute what is the maximum answer in the left hand side and what is the maximum answer in the right hand side. Okay, maximum path sum in the left hand side and maximum path sum in the right hand side. So calculate that, left recursion and right recursion. After that, including this current is going to be equal to what? Current plus left plus right. Okay, so this is like the current path. So for this element, it's going to be this thing for minus 10. Okay, then it's going to be like, okay, this is the path that this path sum that I have for this particular node that I am right now at. Update the global one. Update the global one, right? Sounds good. Similarly, if you had some more items over here, let's say 16, 3, 5 or something like that. Then for 20, for example, it will be like, what is the maximum path I can get in left and right, and then plus 1. So that is a current maximum path, including 20, like in 20. But for when you go above, for 10, you have to be like, okay, what is that going to be? What is that current path? Current maximum path? At the current node, basically. Not including the current node, but at the current node. That is maximum of left and right plus current. It's exactly the same like the diameter one. That's it, question done. Simple. So I start from 10 and I'm going to be like, okay, go in the left, 9. So here the maximum I can get is 9. I will remove this for now. Maximum I can get is 9. Okay, this will return 9. Okay, sounds good. And then this will be like, this will return, this will now go, okay, right hand side 20, left hand side 15, this will return 15, this will return 7. Then the maximum path including this node I can have is maximum of 15 and 7, which is 15 plus 20, 35. This will return 35. Sounds good? Okay, but while you're doing that, you're also calculating. So there are two things. This thing is calculating the path with max sum starting from the current node, but you will also be calculating at every stage. Let's say 15 and 7 was returned. So when it was returned, you will calculate 15 plus 7 plus 20, which is this path sum also. And that you will keep updating with the global one. So 15 plus 20 plus 7, which is 42. So let's say global first was 0, then it became 9, then it became 42. Okay, then it will be like, okay, 9, 35 and minus 10. So if I include this path, 9, 35 minus 10, 9, 35 minus 10, what do I get? 9 plus 35 minus 10, 34. Is 34 greater than the global maximum? No, it's not, so I will ignore it. But the maximum path here will be returned will be maximum of 35 and 9, which is 35 minus 10, 25. So the overall answer 42. Okay, easy, simple. Traversing space and time complexity same, not changing. Simple question like the diameter one. There's one thing I think that we may have missed, which is what if a path gives me negative number? I have to ignore that. Some path can give you negative numbers because it says it has negatives in it. It's simple. If you get negative number, ignore it. I don't want to take that path because it's negative in number. Simple. Facebook question, hard, very popular, but in reality very easy. Okay, I will copy paste this, zoom out a little bit, maximum path sum. Int answer is equal to 0. not 0. Integer dot min value. Here I will say helper, and I will pass. No, I don't have to write helper. I can just do the left right traversal. Yeah, I can do that. I will just call this node, and I will say if node is equal to null, return 0. Oh no, I need a helper because I need to return answer. Helper root return answer. Int helper tree node. That's it. Node is equal to null, return 0. What after that? Left recursion, right recursion. Okay. Helper, sorry, int left is equal to helper of node dot left. So just left recursion. The recursion is made for this so that complex problems can be solved easily. Then the maximum, if I'm including this, is equal to what? Left plus right plus node dot value, and say path sum. But global maximum that I have over here is answer. Answer is going to be equal to math.max answer or the current path that you have, which is path sum. And then what is the maximum sum of a path that I can have from that particular node, which is max of left, right, and plus current. Current node dot. I've already explained how this works. I did the entire thing, you see, red and blue ink. Okay, but if there is a path in left and right that is negative, I will ignore it. Okay, so I can say left is equal to, if it's negative then just make it 0. So I can say math.max of 0 and left. Similarly, right is equal to math.max 0 and right, because if the sum is negative of the path, it will no, why would you take it? It's going to reduce your overall answer. Submit. Oh wow, this was hard question, but beats 100% of Java users. A very fast solution. Okay, cool. O of n time complexity, very easy, cool stuff. If it's not a balanced tree, then maximum space it can take is O of n also. But yeah, someone asks you about space-time complexity, you already know that. Done a video on it already. Very cool, very nice. So hard question also done. Feel like you need more because this is the only tree video I'm making. Okay, I will not make any other. I will make one other because that will contain using tree with hash maps and heaps and stuff. But this is the main video for trees. This is where all the questions will be asked from this video. So yeah, let's do a few more and then we'll wrap up. But yeah, check out the assignments also. I will not leave you. I'll do everything. Okay, I want to make sure that tree is one of the topics you do like this. Okay, now let's look at some more path problems. These are going to be a bit more challenging, and it's night now. See, this is why it's so difficult to complete the playlist, because it takes so much research, so much time, entire days just to make one video. But anyway, new question. question is, you are given a tree, okay, 3, 5, 9, 10, 12, 16. You're given an array that contains a path, something like 3, 9, 12, 8. You have to see whether this path is existing in the tree or not. Again, top down, so you know depth first search will be used. 60% question is solved. Very simple question, just like the path sum question we did. Very simple. I will start from here, okay, and I will check if this is the leaf node or not. It is not, so I will move forward. I will go on the left hand side. As I go on the left hand side, I'm actually going to, one thing I know is it's from root node to leaf node, so it's easy. Root to leaf is easy. So if I know I've started from 3, I know 3 should be here. I can maintain an index which is equal to I is equal to 0 in the middle, in this beginning, and here I can maintain a level. Okay, don't have to maintain a level, I can just move ahead as I go forward. So here I am at index I is equal to 0, or level is equal to 0, or whatever you want to call it. So this 3 should actually be equal to the index value of 0 in this array. Yeah, it is. Okay, now move forward. 5. Here the level will become 1. So I of 1 should be equal to 5. It is not, so return false. Okay, this is not working. Go on the left hand side, right hand side, 9. I of 1 should be 9. Yeah, that is correct. Okay, move forward. I of 2 should be 10. Okay, return. This will not work. False. Then on the right hand side, I of 2, 12. Yeah, it is correct. I of 3, 8. Yeah, that is correct. Return true. So either true or false. Either you get in right or left. So true or false will give me what? True. True or false will give me true. True or false give me true. True is the answer. Yeah, I have found a path. Okay, very simple. Very simple. This is easy question. I think you can do it, but still I'll code it, no problem. So here I can say, this is also O of n, but find path. Node int array. Okay. My base condition, if node is equal to null, I'm going to say return array dot length should be equal to 0. Otherwise I'm just going to say return helper function node array, and I will initially pass level as 0 over here. 0 first. Boolean helper node int array int index. Initially index 0, but base condition, if node is equal to null, I will return false. Okay. Otherwise, if the index becomes out of bound, or it is not equal to this value, so 3 is not equal to the index, the array of 0, 5 is not equal to array of 1, something like that. So whatever index you are at should be equal to that node. Node dot, no, I can say if index is greater than equal to array dot length, or node dot value is not equal to array of index, return false. Otherwise, when will you return true? We will return true at the end. If this is the leaf node and it is also the end of the sequence. So if node dot left is equal to null, and node dot right is also equal to null, and the index value is equal to array dot length minus 1. Array dot length minus 1. In that case, return true. Okay. Otherwise, recursion calls, either left will have answer or right will have answer. Node dot left array index plus 1, or node dot right array index plus 1. Yeah, that's it. Done. Try to run it and debug, do whatever you want. Okay, let's do some more difficult questions. So here I will saying that we already did one, but here it's saying route to your leaf, and we had a path, right? We did the path sum problem, which was the first problem we did in sum. So this one, the very first one, this is also route to leaf. But what if we want to count every path sum? Not just route to leaf, but any in the middle, anything can work. All the path sum. So how many such answers exist? Let's try to see that one first. Okay, so for example, I have something like 1, 3, 2, 1, 3, 2, 2, something like that. I want to find the sum, how many answers exist for 4. So that's 1, that's another one, no, 3 is fine. That's another one, 3. And I can also keep it like, you don't have to have route to leaf. So I can put 11 here or something, 9 here or something. So you can see route to leaf is not there. Some route to leaf is there. Let's say some route to leaf is there. Some not even route to leaf is there. 16 and something. Multiple paths can exist. How do we solve this problem? Now that's a good question. Pause this video, think about it. It's actually very simple. So you know, whatever path you are at, it can have multiple answers. So I know depth first search will be used. Hint number 1. So I start from here, and let's say I try to store my current path somewhere in a list, or let's say I have some current path. Let's say currently it's 1. Can I make 4 from 1? No. Then I go on the left hand side, I'll have 3. Then it's gonna be like, okay, in this list you have 1 and 3. 1 and 3, how many ways you can make 4? 1 ways via which I can make 4. 1 ways. Okay, so this I will return 1. Then I go on the right hand side, then I will add 2 over here. But see, now when I'm going on the right hand side, it still has answer from the previous trees, which is wrong. How do we solve this problem? We have done this. Backtracking. So when you go back, make sure you remove your answer. When you come out of the function call, remove your answer. Hope that is clear. Please, you have been studying this video for I don't know how many hours now, but it should be clear to you. Backtracking. See this example I gave you? Backtracking? Okay. Then add 2 in over here. I showed you what will happen if you don't remove 3. It will have 1, 3 and 2 as a path, which is nothing. How can you do that? It's only in one line. You cannot go backwards. Okay. 2, 1, 2 makes 4. No, it does not. Then I'll go on the left hand side. 1, 2, 1. Does it make 4? Yes, it does. So only one way via which it does make 4. Okay. Only one way. I will keep going. It has 1 for now. Okay. I can take a counter over here. This will have 1 over here. Okay, like how many paths I have. Then I go inside. 11. 11 be like, okay, nothing. I am not getting anything. 0. Return. Now when it goes back, 11 should be removed from the stack. Backtracking. Now write nothing. So only 1 is remaining. So it will return 1, but it will also remove 1 from the stack. Backtracking. Then 2 will add 3. Then I will add 2. Then I will again add 2. Now using this array, how many paths are there that can form 4? There's one path here that can form 4. It's 1. I'll add 1 over here. 16, nothing. Backtrack. 2, 2, nothing. 1, backtrack. Backtrack. 3, backtrack. It will return 1. So left plus right answer. Left plus right, which is 2. It will return true. 2. Left and right answer 3. Total answer 3. Yeah, good. Easy. Only thing you have to figure out, you are given this list. How do you find all the possible paths? All the possible paths, how do you find that? That is going to be tricky. So good question. Good question. But let's at least do the basic one. So here I will say int count paths node int sum, that is required, and I will say a list of, let's say I create in a list of integers with my current path. I say new linked list. Then I will say return helper node sum path. Int helper node int sum. Okay. If node is equal to null, no path exists. 0. Otherwise, I will take this number and add it in the path. Since I have passed this as a reference, so any change I make will change the original one. I'm not creating copies. That's why I need to do backtracking. So many basic concepts are being used here. Path.add node.value. After that, I will say int count is equal to 0, int sum is equal to 0. Like how many paths can I make? How many paths I can make, I will calculate it here. But after that, I can just say count plus equal to helper of node.left sum path plus helper of node.right sum path. So whatever answer you're getting from left and right, count plus equal to, that is the answer. But when you return the path, before you return count, you have to backtrack, because I'm not creating copies of path list. It is the original one being used. So that's why backtrack. Path dot remove last one. So path dot size minus 1. How many paths I can make that I have to calculate? How many paths I can make that I have to calculate? Since I am coming from top to bottom. Okay, so I had something like this over here. See, I am coming from top to bottom. So 1, 2, 3, 2, 2. 1, 2, 3, 2, 2. I am going to start from this side. So 2, 2. I'm not going to start from 1, 2, 3 because that is already being checked. I have done that already. That is from where I am coming from. So I'll start it checking from the lower bottom. So 2, 2. Not again start from 1. That doesn't make any sense. Hope that is clear. Because I already had 1, 2, 3. So why would I want to start from 1, 2, 3 again? No. I'll start from behind. 2, 2, 3, 2, 1. For that I can create a list iterator. List iterator. You can check the list video or you can just check the documentation. It's just easy. I can just say itr is equal to path dot list iterator. So I can now iterate open it. So I can say while it has a previous. So iterator dot has previous. I'm going to say okay, there is a previous over here. So path sum that I have over here plus equal to the iterator dot previous. Okay, and if this sum that I have becomes equal to the, oh no, I can't have it as sum, I will have it as s, is equal to the sum that I have provided. So while means 2 plus 2, so now 2 plus 2 4. Is this 4 equal to the 4 that I have provided? Yes, then count plus plus. Okay, that's it, done. Yeah, that's the question. So the main question now is, what is the space and time complexity? Space complexity can be height, should be fine. No, but we're also taking this thing, O of n, or O of, like in the worst case, or O of height in the best case. But again, in the best case or worst case, if we talk about time complexity, then n for the recursion, and this internally, in the worst case, if the tree is not balanced, can take n. So n squared is the worst, but if it is a balanced tree, then this will be height. See, it's going till the height, which is log of n. So n log n if the tree is balanced, n squared if the tree is not balanced. Time complexity. Space complexity O of n, worst case O of log n, best. Okay, done. That was it. That was the question. Simple, easy. Okay. Cool. Now another similar question is that this is the last one that we do because it's we have done almost every single concept. So you are good to go for trees interviews, but make sure you practice. Otherwise, you are good to go now. That was the main motivation I had. Some typos here and there, but you can fix it. Okay, one more question, then we move forward. Let's do the same question, but instead of counter, give me all the paths. I will be like, Kunal, please leave us alone. What are you doing? Why are you complicating things so much? That's how you study. You are able to solve one question, try to improve it. Okay, what if I change this thing? What if the interviewer says, don't give me the number of paths, print all the paths. Let's make it more complex. Save every path in a list of list. But think about it, is it any different? Here you're taking a counter, instead of taking counter, just put it in a list. Just put it in a list. So I can say copy So logic will be same, but I'll put it in a list. Put in a list. Okay. So I will create a list of list first of all. Paths. Okay. List of list. This will be find paths. Create a helper which will have a node, sum, my path, and my entire the paths so that I can add it in the main answer. Okay. But I have to have a current path also. New linked list. New array list. Think it will be array list. Array list. Array list. It should be array list. Okay. Array list. Don't know why I took linked list. Okay, no problem. So you can see logic wise nothing is different. The only thing is instead of count, I need to return list of list. I'm not returning anything. Okay, oh no. Yeah, I'm not returning anything. No, I'm returning it here. And I will just call the helper and I will just return paths. Yeah. Helper is not returning anything. It is changing the main reference variable object that we have. Basic object-oriented programming. Okay. If node is equal to null, 0, I can say path.add node value current path. I don't need the count. I don't need the sum. How do I know that I have found the path? I can say if it is a leaf node. So if I'm trying to find all the paths, for example, let's say from the root node to leaf node or whatever, trying to find the same thing. But if you want to find all the paths that are not from root to leaf node, you can use this while condition. That you can do on your own as well. But if I'm saying if node dot value is equal to my sum, and let's say if it's a leaf node, node dot left is equal to null and node dot right is also equal to null. In that case, in my paths, I can add the answer. Easy. So this is only for I'm doing just to explain to you. I wanted to explain to you list of list how that will work. I think this thing should be clear to you. I'm adding void over here because it is directly making change in the object created in this find paths method. Okay. So that way I don't have to return anything. It will automatically change this. But if it's asking you return a list of all the possible paths, not just from the root node to the leaf node, then I have already taught you that as well. I have taught you that. I have not skipped it. You just did that. You just did it in a count format. Okay. Done. Otherwise, left tree and right tree. So I will say helper of node dot left sum minus node dot value path and paths. This is how you know that we are not really doing anything with the other things, because I'm not changing the argument in the recursion. So it's only acting as a reference to the one in the other function. It's actually very simple. If you have solved my recursion assignment, you will understand. Then write subtree call. After this, I am going to backtrack for the path that I have right now here. Paths.remove, path.size -1, not returning anything. That's it. Done. That's it, yeah. So if you want to do not just from root to leaf, but also in the middle, then in this same function, you can add in that while condition and it should be fine. Time complexity for this is what? O of log n space complexity as well. Because we have a copy that we are storing here. See? And the copy we are storing is of the path for n nodes. So what is the maximum in a balanced tree? What is the maximum path from root to leaf node? Log of n. Total number of nodes are n. So n log n space and time. Okay, now let me show you something cool. This is like the top 50 tree coding problems for interviews on GeeksForGeeks. You can check out my assignment in the description as well. Lead code is like more than enough. And you can see level 1 problems. Level 1 you all can do like this. Well, all the levels, easy, medium, hard on this top 50 or top 100 or top 500, no matter what people give you. You now know that Kunal has taught us a few problems. Using that we can solve any problem. Height of the binary tree. Determine if two trees are identical. Mirror of the tree, I think we did this one. Symmetric tree, did this one. Diameter of a tree, check if it is balanced tree, did that. Children sum parent something, no problem. Check for binary search tree, array to binary search tree. Maximum GCD of siblings, we already learned about siblings, so you can do GCD now. Largest value in each level of binary tree. Remember we did what did we do? The average of every level instead of average. Try maintaining the largest value. Zigzag tree traversal, oh we did that. In order successor, no problem at all. Kth largest element in a binary, yeah we did this. I told you multiple approaches for this. Level 2, check if a subtree, you can do that. It's also a traversal problem. Single value subtree, unique binary search trees, in order traversal, preorder traversal, post order traversal. Yeah, it's pretty cool stuff. One thing I think I wanted to mention was that we have learned about recursion, right? Let me show you something. One thing I want to mention is that we learned about breadth first traversal, and you can use recursion using, you can do it using recursion also, but I taught you the iterative approach also, which is using queue. And we did the depth first traversal, and we did that using recursion. Now, one thing I told you in the recursion playlist is that every recursive program that you can write it in iteration also. And I told you the reason, because it is easy to solve problems in recursion. And once you have solved it in recursion, to make it more optimized, you can convert it into iteration. And how can we convert recursive problems to iteration? Using stacks. So one last thing I want to show you is depth first search using stack and not recursion, and how that's going to be beneficial, because we're not using stack, so no stack overflow. So let's get started. Let's see that. It is actually very simple. If I'm talking about DFS using stack, so let's see how we can do that. So if I have like, and by the way, you can convert all the questions using it, but ideally I would say to keep things simple, use recursion. Okay, it's fine. If there is a way to optimize the recursion, that's dynamic programming, but not all cases can be applied. Like for these three problems, not really. But if there are some problems like the string ones, maze ones, where you can store some sort of data, I think in some of the cases, like with graphs and trees as well, like many cases in fact. So that's something for later on. But I think for interview preparation type, whatever I have taught in this video, for FAANG type interviews, more than enough and highly optimized. So don't worry about it. Because we did all the questions O of n and O of n time space mostly, right? So it can't get better than that. DP will also take extra space only, but a little bit more efficient if you want to make it. Depth first search using stack. So tree is given 12, 3, 9, 5, 6, 18, 4. So depth first search, let's say I am starting, obviously I'll start from root node. Then I will just take a stack and I will put it in the stack. That is what I will do for now. Similarly, we do with Q in breadth first search. We already saw so many questions. I think you will be pro in that now. But similarly, how we have solved all questions using Q, this you can solve using stack. No real benefit. Don't confuse yourself too much, but still if you want to do it. Time complexity space complexity is fine. O of n, it's more than enough. Good. So what I'm going to do now is, while my stack is not empty, I will keep removing from it. I will remove 12, print it, and when I remove something, I will add its left and right child. So I will add 3 and I will add 9. Okay, but now 9 will be removed. I wanted 3 to be removed. I want left child first. Let's say I'm doing preorder, node left right. So I will add right first, then I will add left. Then 3 will be removed, 3 will be printed, and 6 and 5 will be added. Then 5 will be removed and nothing will be added. 6 will be removed, 4 will be added, 4 will be removed. So see, pre-order traversal. And then nothing will be added. Then 9 will be removed, 18 will be added, 18 will be removed. Done. Easy. That's it. Okay. Maximum amount in stack can be height in a balanced tree. Visiting every node once. Time complexity O of n. That is why I did not teach you this one, because no real benefit. But still, if you want to, no problem. Okay. Shall we code this? I think you can code it on your own, but I will still code and show you. Okay, so here I can say DFS using stack. If node is equal to null, just return. Otherwise, here I can see I will add my first element, but before that I need a stack. Node type stack is equal to new empty stack. Stack dot push my node that I have passed, which will be root node for starters. Then while my stack is not empty, what I'm going to do is my node removed will be equal to stack.pop, and I can print this. Okay. After this, I will check whatever I have removed, if it has a left and right child. So if remove dot left is not equal to null, left, but I am going to push right first for the obvious reasons that I mentioned, because I'm doing pre-order traversal. I think that is it. Yeah, that's it. Should you use it? No. Recursion is fine. Time complexity, space complexity is okay in that. Very good. Not okay. Great. And yeah, that's pretty much about it. Okay. So other questions, as you can see, all these questions you can do like this now. That was the beauty of this video. I don't want to make like every single video, like I will say tree series 60th video, tree series 70th video. No, it will not help you. It's too slow. I don't like doing that. And it's not really building the intuition. Construct tree from pre-order traversal, very easy. You can do other yourself as well. Minimum distance between two given nodes, think we did this. maximum sum to leaf to root path, did so many path questions. Odd even level difference, what is this? Level means breadth first search, very easy. Lowest common ancestor, oh we did this from scratch, we did everything. Ancestors in binary, you can check it out yourself now. Outside the given range, remove the binary search tree keys. When we talk about deletion, I told you, for deletion we do the not pre, not in, post order. Yeah. Obvious examples I gave in the start only of the depth first search section. Pair with given target, you have to find pairs, easy. Some tree we did this. Heap we have not done right now, but we will do heaps in the next videos. Clone binary tree with random pointer, maximum sum of non-adjacent nodes, easy. Extreme nodes, alternate order. Level 3. Linked list. Oh, linked list questions in binary search tree, we did so many. Sorted linked list to binary search tree, not a problem. Binary tree to double linked list, not a problem. Nodes at a given distance, we did this. Connect nodes at the same level is level 3 question. We did this today. Maximum sum paths between two leaf nodes, easy, we did this. K sum path, we did this. Merge to binary search tree, you can do it. Number of turns, you can do it. Fixing two nodes, burning binary, so and so forth, whatever. I highly recommend going to the GitHub repository. All the links can be found in the description. 13,000 people have started, you can do it as well. Assignments will be updated here. Lecture notes will be updated here. As you can see, I've already updated the trees assignment. So many questions. But yeah, I am saying it again and again. Again and again I'm saying this. Lead code for your coding preparation is more than enough. Again and again I'm saying this. Okay, there's so many trees question on lead code for free you can do. Or if you still, let's say, exhaust your lead code list, then you can Google random questions like best tree questions or whatever. But you will not be required to do that because there are more like thousands and thousands of questions on lead code. Your entire college year will go by. So try to do that. Lead code. More than enough, nothing else needed. DSA sheets, waste of time, not needed. I made a video on that already. So yeah, lead code and my assignments, more than enough. And practice, keep practicing. Cool. That was pretty much about it. And I worked so hard for you people. So my only ask for you is the easiest thing that everyone can do. Easiest thing is like and comment and subscribe. These 3 things. Like, comment and subscribe, you can do. It's very easy. So easy. I don't need your money, but like, comment and subscribe is something you can do right now. I worked so hard for you. So because I'm telling you this because it will help the video get more views and more people will watch it. Okay. Ad revenue, trust me, it's not that much. My most popular video is the patterns one, which is close to 2 million views. The ad revenue on that is embarrassing, literally, because the Indian audience so don't get that much in India. It's really embarrassing. But anyway, like, comment and subscribe you can do. It will not take much time. If you want to go above and beyond and help me, you can take a screenshot and share it with hashtag DSA with Kunal or tag me on Twitter and LinkedIn. Write a nice little post of around how trees help you. If this is helping you clear any interviews, reach out to me, Kunal at wemakedevs.org, and tell me. I'm happy to add you as a testimonial in our free community, and it will only motivate me to bring more and more bootcamps, more and more courses. So like, comment and subscribe is the easiest thing that you all should do. And for other people who want to help out as well, some additional thing you can do is taking screenshots, sharing on socials, writing a thread what you learned, or suggest some just write it in such a way that other people will watch it. So be enthusiastic when you share. I'm happy to interact with you, answer questions over there. But yeah, that's it. That's all I wanted to say. I trust you that you will do it because the video was so good and it was so long. Lastly, assignments can be found in the description below. Code can be found in the description below. So using my link, you can like sign up and stuff and directly fork the code that I have written so you can run it on your system. It will make it easy for you to use the code that I have written on the browser, so you can check it out on your browser itself. But assignments, notes, everything can be found in the description below. And comments, if you have, you can leave those comment section below as well, but do comment anything, appreciation or whatever. Lastly, I mentioned to you about sharing. Next video will be heaps, hash map, then dynamic programming, graph, and small topics like tries and greedy and sliding window and stuff. So even my voice is breaking down now because I've been speaking for a few hours. But I think that's pretty much about it. Yeah, lastly, code link, sign up on the platform, whatever, all the things in the description below, and GitHub repository, assignments. And yeah, lastly, I'd just like to say this was it. You will be able to solve any tree interview question now. I've taught you everything. I've researched for the past 10 years of questions, what sort of questions these big tech companies like Google, Facebook, Amazon, Microsoft ask. And I created this video for you. So remember, it is not advisable to watch videos that are just individual questions and topics. That will not help you. They will only teach you how to solve that individual question. This video, on the other hand, is building thought process. Now, using these limited questions that we have done, which I think is quite a lot, if someone gives you a newer question, you will be able to do it. So, watching individual questions playlist, not very beneficial. It is spoon feeding. But watching intuition based questions like this that I have done, just one video, happy to help. But yeah, if you want to learn more about trees, you can check out the trees theory, but this was a question specific video, the types of things companies ask. And yeah, good luck for your interviews. And I'll see you in the next one. If you want to check out previous DSA videos, comments, links, everything, just check out the description. Yeah, all the links are there. And yeah, comment, like, subscribe, and share on socials. See you in the next one. Have a great day. Bye.